All right, good evening, everyone. I've got 6 o'clock here. My name is Jason Dunn, and I am going to be giving the basic radar interpretation presentation to you guys tonight. Hopefully, you can hear me okay. If you're having any questions with or problems with your audio, you can check your speaker connection, or you can ask David a question here in the question box off to the side. You can pop that out here, and I will let David talk a little bit about that question box where he's going to be answering questions live as we go through this. So David, you want to talk about that a little bit?
Yeah, give me a second. Sorry. All right, so I'm here in the office. My name is David Bonnet. The questions box. So if you see the question, if you type in any question, then I'm here to answer basically anything you got. If it's about what Jason's talking about, if you want a little bit more of an in-depth answer, or you want some additional resources, whatever the case is, then go ahead, type your question in, and I'll be the one answering back to you. At the end of it, or basically at any time, if you wanted to save off the questions log, then you can go to File and then Save Questions Log, and what it'll do, it'll save it as a text document, so that way you could keep it for reference. So you could either do that at the end of the call, wait until we're finished, or you can do it at any time. If you ask a question, you want your answer saved, then go ahead and do that. But like I said, I'll be here answering all the questions, and hopefully I'll make my fingers numb with all the questions. I'll be here ready.
All right, thanks, David. So we'll go ahead and get started with this. I've got 100 and some slides, and anyone who's ever listened to one of my radar presentations knows that these always end on time, and we'll get out of here. So I'm going to try and hurry up through some of this basic stuff so that we get out of here before midnight or so. We'll go ahead and just give you a brief overview of what we're going to talk about this evening. We're going to quickly go over some radar fundamentals. We'll talk about base and derived products, and then we will discuss the warning decision process at the National Weather Service. So I'll give you a little bit of an overview of some of the products that we're looking at and the process that we go through to issue warnings. We'll talk a little bit about squall lines, bow echoes, and some miscellaneous stuff. And then David can answer some of your questions. We'll also take a couple of breaks too, here and there. And if you have any other questions, or if David wants to bring something up that we can discuss, we will go ahead and do that. What can you expect from this presentation? Well, you're not going to be an expert at the end of this talk, an expert in radar interrogation, but hopefully you will come away with a better understanding of some of the products that are available out there and how to use them. Over the years, radar has become available. Pretty much everybody has it on their phone. If you're joining this presentation, you probably look at radar all the time. So this presentation will hopefully give you a little bit better understanding of what it is you may be looking at. Okay, about radar. Radar has been around for a long time. It's actually an acronym, or used to be, it's a word now, but it stood for radio detection and ranging. And over the years, it has become the most effective method for the detection of precipitation. It is a remote sensing tool that we use. And so that means that we are not directly observing the atmosphere, we're actually doing it remotely. The early technology has been around since the 40s. Precipitation echoes were first detected around 1941, and then the technology kind of rapidly advanced from there. Electromagnetic energy is transmitted out at the speed of light, and it is bounced, hits a target, and some of that energy is reflected back to the radar. So that's where the term reflectivity comes from. Like I mentioned before, it's been around for a long time. The image off to the left here is an old radar image from the 1960s, so about 60 years ago. You can see in this image, you can make out the supercell shape there, a nice little hook echo. We've got some ground clutter. And then this is a much more recent image from the 2000s, where you still see the nice supercell storm that we have here, nice hook echo, and the little debris signature here at the end of this hook. So the the images themselves haven't changed over the years, just the technology has gotten a little bit better. So let's talk a little bit about common weather radar bands, and we'll talk a little bit about some of the radars that you'll see in this presentation. Common weather radar bands. This presentation will mostly focus on the Nexrad radar, WSR-88D. That is an S-band radar with a wavelength of around 10 centimeters. And we'll talk a little bit about why that's important. You will, as you go up farther in this band, you'll get into the C-band. These are higher frequency radars. This would be our terminal Doppler radars that are at the airports. A lot of television stations own C-band weather radars. They have a little smaller wavelength. And if you look at the picture here, the dome itself is usually smaller. The antenna is a little bit smaller. You keep going into the X-band, and this would be radars like our CASA radars. We'll talk a little bit about those. These are small wavelength radars, but they give us really high resolution pictures of storms. Now, the importance of understanding these bands is that as you get into C-band and X-band and the wavelengths of the radars get shorter, they will attenuate more. So that means that when the radar pulse is going through very heavy rain, it will get absorbed by whatever it's traveling through. So if you've got satellite television at home and you know that it rains really heavy and your TV signal goes out, that's signal attenuation. So these radars that operate in the C-band and the X-band are much more prone to attenuation than an S-band radar. And that's why the Nexrad network operates in the S-band. Is it makes a really good surveillance radar to go through very heavy rain. And then you get farther down on here, and there's other specialty radars. This is a cloud radar, which has extreme attenuation. It doesn't even really get through clouds. So a little bit more about the Nexrad. It is a pulsed Doppler radar. We'll talk about the importance of a pulsed radar. Has a wavelength of 10 centimeters. The antenna inside this big dome out here, and the Fort Worth radar is located down in southern Tarrant County at Spinks Airport. We also have the Central Texas radar near Fort Hood in Granger. And then we have access to several other radars, Shreveport, Frederick, Dias, but they're all built the same. They all have an antenna inside this big dome. That antenna is 28 feet across. The radars transmit with a peak power of 750,000 watts. It is a dual polarization radar, and it's a simultaneous transmit dual polarization radar. That means we don't actually have two transmitters in there. The pulse goes out at a 45-degree angle, and then we receive a horizontal and vertical channel back. So the Nexrad itself is an excellent long-range surveillance radar because of that longer wavelength. It can get through very heavy rain, go through multiple storms, and still give us a good assessment of what's going on. Has low signal attenuation. We do volumetric scanning with the Nexrad radar. And one of the better things about the Nexrad radar is its excellent signal processing. So the data quality that we get back from the Nexrad is really top notch. Now, the downsides are they're large and costly. They're expensive to maintain. They have to have regular upkeep, and when they go down, they have to be repaired. We have to get people out there to repair them quickly because they're part of the network of radars that keep an eye on the weather. Resolution is not as good as you'll see in a C-band or an X-band radar because of the longer wavelength. And because we do volumetric scanning, there can be long wait times between the low-level scans. So when you pull out your phone and you're looking at your radar, you're probably looking at the lowest elevation angle, and that elevation angle may not update for 4, 5, 6 minutes or so, and it's because it's doing volumetric scanning. So what exactly is volumetric scanning? Well, we have a storm, and the radar is going to scan out down low, and then the antenna is going to raise up, and it's going to continue to raise up. We scan 14 elevation angles in about 5 minutes. And if you look at the radar image off to the left there, you will see that as the radar scans up, we get a different look at the storm as the antenna goes up. That's important because we need to not only look at what's going on near the ground, but we need to see what's going on in the mid-levels of the storm and the upper levels of the storm. It gives us a good idea of how fast the storm is strengthening, how large hail may be. It gives us an idea of how strong the updraft is, all kinds of information that we can get out of a volume scan. Now, this image here isn't particularly useful, but it will kind of give you an idea of what a complete volume scan looks like overlaid on top of one another. And we have to keep in mind that the Earth curves. So when you get farther away from the radar beam gets up a little higher. So you're kind of looking in this little bowl, if you will. And then you can see the individual slices going up all the way up to around 20 degrees in elevation. We can also lay these out horizontally here, and you can see we have really good low-level coverage. The angles kind of overlap one another. Gives us a good look at what's going on down low and in the mid-levels of the storm. And then we do scan up higher away from the radar as well. That's important when we have storms close to the radar. So we need to look up a little bit higher if you got a really tall storm. But there are some gaps in the coverage aloft that we kind of infer what's going on in between those. So this is the reason why we do volumetric scanning as opposed to just one single look down low. There's a lot of information going on up in these upper angles that we need to kind of assess for tornado detection and large hail and things like that. A couple other things to consider. The radar beam is not a laser. It is more of a cone. So when the radar pulse goes out, you have the beam center line, and then the beam itself is defined by where the power drops off by half on either side. And for the Nexrad radar, that's about 1 degree. But power will actually go out all the way around that cone in all different directions. And so it's not a laser beam, it's more of this three-dimensional cone. Now that's important because as we get farther away from the radar, that cone spreads out and it can affect how we see storms at different ranges. The Earth curves, the beam spreads out as you get farther away. So at 120 miles, that beam is over 2 miles wide. So what does our radar coverage look like in North and Central Texas? If you can see the map here, we have these green circles here, and if you live in any one of these green circles, you have radar coverage below 4,000 feet. And so you can see if you live in the Metroplex here, anywhere in the Metroplex, you've got radar coverage below 4,000 feet. Central Texas near the Granger radar, out here by Dias, here's Shreveport. If you live in the yellow area, you've got radar coverage below 6,000 feet. And if you live in the blue areas here, you have radar coverage below 10,000 feet. Now, if you happen to live outside of these areas here, a little farther to the east, say Paris, for example, up in Lamar County, there is no radar coverage below 12,000 feet. That's gotten a little bit better. It used to be 14,000 feet, but they added a lower elevation to the Shreveport radar. So now we can see down to about 12,000 feet. Palestine is around 10,000 feet. There's no coverage below that. But if you live in the Metroplex, you're pretty well covered. We have not only the Nexrad radar, but we've got 2 terminal Doppler radars, 7 CASA radars. We've got all kinds of radar coverage in the Metroplex. I-35 is covered pretty well. If you live in Central Texas, you've got very good coverage here. Waco is about 5,000 to 6,000 feet, which is pretty adequate. It's just mostly our eastern areas here where the radar coverage kind of drops off. So the effects of that Earth's curvature. So let's kind of draw this up hypothetically here. We've got two storms, and these storms are going to be identical. One's going to be approaching the Paris area, which is 120 miles away from the Fort Worth radar. And then this storm is going to be rotating. We've got a strong mesocyclone associated with it, and we're going to sample it from the Fort Worth radar. And you can see that from Fort Worth, our lowest elevation angle would hit this storm at around 14,000 feet. Now, Shreveport might hit it around 12,000, but our radar hits it around 14,000 feet. Our second elevation angle would hit it at around 20,000 feet. The same storm over Weatherford, for example, which is only 25 miles away from the radar, would have multiple elevation angles that sample through this very strong rotation. So the same storm that they look identical, they have the same strong rotation with them. One is going to look very different on radar than the other one. And we have to keep that in mind and make those mental adjustments as we get farther away from the radar. So what would it look like on radar, these same storms, if we scan them and looked at the velocity data? Now keep in mind that the beam spreads out, and at 110 to 120 miles, that beam is about 2 miles wide. So we hit these storms and we get back velocity data, and it would look something like this. The storm that's close to the radar, we would hit multiple times, and you can see the bright green colors. We'll talk about the greens and the reds here in a little bit, but you would have very good velocity data from the radar scanning at this range. Now, that same storm that has the same rotation at 110 miles would look very differently on radar. Because the pulse volume or the beam itself is wider, some of those higher velocities are going to get skewed downward just because of the large pulse volume. So your bright greens and reds that may look like this on the close storm may look something like this at 120 miles or 110 miles away from the radar. So we have to kind of keep that in mind when we're looking at velocity data at range from the radar, at great range from the radar like that. So that's just one example of how beam spreading can affect, say, rotation within a storm, our analysis of rotation within the storm. So let's talk a little bit more about some of the terminology you may have heard. AVSET, I don't know if you've heard much about that, but basically it's Automated Volume Scan Evaluation and Termination. We love our acronyms in the Weather Service. Everything is an acronym. It's a fancy way of saying, hey, if we don't detect anything up high, let's terminate the volume scan and start over. And that's important because if we don't have anything close to the radar or anything up high, then terminating that volume scan can save as much as 75 seconds of total time in the volume scan. Now, minute and 15 seconds is a long time when you're interrogating radar. A lot can happen in a minute and 15 seconds. So AVSET is really, really helpful, especially when we get thunderstorms that are just developing or off to the west. Now, it won't terminate the volume scan if there's storms, you know, on top of the radar or anytime it detects something up all the way to the highest elevation. But nonetheless, AVSET is always enabled on the radars, on our radars, and can save scan time when there's nothing going on aloft. SAILS is another one that you may have heard. SAILS stands for Supplemental Adaptive Intra-Volume Low-Level Scan. That's a mouthful there, but basically what SAILS does is it will add 1 to 3 supplemental 0.5 degree scans in the middle of a volume scan. So I'll show you a list of how the radar actually scans, and you'll see exactly what I mean by inserting them in the middle there of the volume scan. But basically, if we're worried about low-level rotation and we need a more rapid update of what's going on at 0.5, we can enable sails and add up to 3 different sail scans to the volume scan. The downside is it will add time to the overall volume scan. So we don't run that all the time. We just kind of run it as needed. The newest addition is something called MERL. It stands for Mid-Volume Rescan of Low-Level Elevations, and they can all be kind of confusing. MERL is very similar to sails, but it will scan up to 4 consecutive low-level elevations. So not just the 0.5, but it can scan 0.5, 0.9, 1.3, and 1.8. Now the difference is it will scan those consecutively. So if we have MERL enabled, let's say MERL 4 enabled, in the middle of the volume scan, it will go back down. It'll scan all 4 of these angles and then return to where it was. All right, let's talk a little bit about that pulsed Doppler radar and something called the Doppler Dilemma. And this is fundamental to all pulsed Doppler radars, but basically it states that there is an inverse relationship between maximum unambiguous range and maximum unambiguous velocity. There is no single PRF that maximizes both range and velocity. So that too is a mouthful. What does that mean? Okay, so the radar, when it's operating, it sends out pulses one after another. And typically when we're scanning the 0.5 degree slice down low, we use a low pulse repetition frequency. It will send out about 300 pulses per second. Now, that pulse has to go out, hit a target, and get back to the radar before the next pulse goes out. If it doesn't, then it will still continue on its way. And if it hits a target, the energy will still go back to the radar, but the radar won't know which pulse it came from. And so that results in something called range folding. Now, when we're trying to just see reflectivity and where the rain is, we want to use a low pulse repetition frequency. We want the radar to pulse slowly. So that pulse can go out really far, hit a target, and come back before the next one goes out. So that gives us a high maximum unambiguous range, and it's really good for reflectivity. The problem is it's really bad for velocity data. So if our target, let's say a tornado, is moving really fast or the winds are really strong, you will have something called folded velocity data or aliased velocity. The radar won't know whether the wind is moving toward or away from the radar because the radar is not pulsing fast enough. So you have an option here. You can pulse slowly and have a high range but poor velocity data, or you can pulse the radar fast and have a shorter range but better velocity data. So that's what it means by there's no single pulse repetition frequency that maximizes both. We have to compromise. We either have good range and poor velocity or vice versa. So how do we solve this problem? Well, the Nexrad does something kind of unique. It does something called split cut elevation. So while you're sitting there at home and you're looking at your radar and you're looking through it and you're saying, wow, this thing hasn't updated in 5 or 6 minutes. Why is this thing so slow? Well, the Nexrad radar is actually doing a lot of work. It's continuously scanning the atmosphere. So that 0.5 degree elevation angle actually gets scanned twice. And the first time that it gets scanned, is something called a surveillance waveform. And here's our pulse repetition frequency, 321, which is pretty low. And you can see it takes 17 seconds to scan that. But look at our Rmax, or our maximum range, 252 miles. So that pulse can go out 252 miles and get back to the radar before the next pulse is transmitted. But if you look at Vmax, that's our maximum velocity, it's only 16 knots, or about 18 miles per hour. Well, that's not real good, because we know winds are commonly faster than 18 miles per hour. So we have good range, but poor velocity. So what the Nexrad does is it says, hey, I'm going to scan this 0.5 degree slice a second time using a Doppler waveform, and I'm going to crank the PRF up to almost 1100 pulses per second. It takes 11 seconds to scan around 360 degrees. Now look at our Rmax. Our maximum range has dropped to 74 miles. So now that pulse can only go out 74 miles and get back to the radar before the next pulse goes up. But our Vmax is increased to 53 knots, or about 60 miles per hour. That is much more user-friendly for good velocity data. And so that's why if you ever look at your radar app and you notice that the velocity data has usually a ring around the radar of purple, it's usually about 75 miles, 80 miles from the radar. That is because of this Rmax being around 75 miles. You'll still get data beyond that. The radar does some pretty cool velocity de-aliasing and range unfolding. It's got some pretty good algorithms to clean up the data. But that's how the radar operates down low. And you can see it does that at 0.9 and at 1.3 degrees. Now, if we've got sails enabled, after the 1.3 degree slice, it's going to drop back down and insert a sail scan. And you'll get the same surveillance and Doppler scans. And then it will go back up to 1.8 degrees. And then it goes and does something called a batch scan at 1.8 degrees. It doesn't do 2 scans anymore. What it does is it alternates between low PRF and high PRF, and that gives us both good reflectivity range and velocity range on those scans. And then it will continue on its way until it gets to 8 degrees, and then at 8 degrees in elevation, it's all Doppler waveform with a high PRF. And because at 8 degrees in elevation, now we're getting really up pretty high, so we don't need as much range in the reflectivity. So when we are operating in a classic VCP, volume coverage pattern, or classic way of scanning when we have storms, and we have sails turned on and we're doing 3 sail scans, the radar will actually rotate around 23 times in 5 minutes and 30 seconds. So you get a new 0.5 degree scan in about every 90 seconds. You get good long range reflectivity, and you get good, decent range velocity data from all of these scans. So that's a typical Nexrad scan strategy, and that's how we take advantage of these different types of scanning strategies to both maximize the range for reflectivity and the velocity data. So that is just kind of a quick overview of basic radar fundamentals. And I will go into the base and derived products here in just 1 second. We're about 30 minutes in, so we'll take just a little bit of a break here. If anybody has any questions, David, that we need to discuss just a little bit more, we can go ahead and do that now. Otherwise, we'll take just about a 2 or 3 minute break here.
Yeah, Jason, I was actually answering a question. So somebody asked, so if you have more data with sails, et cetera, what's the bottleneck? Is it the data coming through the radar, computer processing power? And so you want to explain that a little bit? So what's the downside of having extra sales cuts or things like that?
So the biggest downside to having extra sales scans, well, there's a couple. The main downside is if you had 3 sales scans running all the time, the entire volume scan would be over 7 minutes long. That's great if you are tracking a tornado that's in progress and you need rapid updates down low. It's not so great if we are trying to assess the mid and upper levels of a developing storm, because now we've got to wait for it to finish these sales scans. And let's say we had a storm out around Mineral Wells or somewhere, and we really needed to look at that 6-degree slice or the 8-degree slice. We have to wait about 7 minutes for each new 6 or 8-degree slice to come in. So that's one downside to running sales 3 all the time. The other downside would be just that you don't really, we just don't really need that rapid of updates down low. Like I said, unless we're tracking something that we know is ongoing or in progress. Sales 3 used to also impact precipitation estimation. It doesn't so much anymore now with some of the dual pole products, but it used to kind of hamper that a little bit.
Excellent. That's pretty much it as far as like repeatable questions or a good question if you want to take a break. But it looks like the bottom of your slides are cut off if you want to try to re-share the PowerPoint.
Okay. How far is it cut off at?
Let me see. So on that slide. It's basically just a small sliver on the bottom. On a couple of the slides where you have a lot of text, then the bottom line of text is cut off.
Okay, can you see that line of text there? What am I looking at?
I can see that. It basically cuts off directly at the text bottom.
Okay. I don't think I've got too much. Let me try and reshare this. Hang on one second. How is that? Is that a little better?
Looks to be about the same. It should be fine. I think it's just a handful of slides that have something on the very bottom.
Okay. Well, we'll go ahead and get started again here with section 2. I'm sorry about the cut off slides there. I don't think I have too much text on the rest of them down low. If I do, I'll be sure to kind of explain what's going on there. Most of the imagery that I'm going to show, though, should be right in the center of the screen. So, so we will go ahead and get started with section 2 here, the base products. And this presentation, primarily the rest of it, we're going to really talk about the base products, the products that if I told you I want you to be looking at these products, it's going to be the base products, primarily reflectivity and velocity. If I said you could pick 2 of these to have and the rest of them have got to go, I would want you to pick reflectivity and velocity. We for many years, for half of my career, we only had the top 3. and then in 2010 we got the dual pole upgrade, and then we started getting the dual polarization products in. But reflectivity and velocity are really the workhorse products of the Nexrad system, and that's really what this presentation is going to focus on. So the base products are reflectivity, velocity, and then we have velocity spectrum width over here. Spectrum width is basically the variability of the velocity data. Dual pole data, we have differential reflectivity, which is in the lower left here. A differential reflectivity is the difference between the horizontal and vertical reflectivity channels. And then we have correlation coefficient. We'll talk a little bit about this one. This one does have some utility, just for average users of radar data. We'll talk a little bit about that. And then specific differential phase. Specific differential phase is basically a measure of how much the beam is being slowed down as it travels through whatever it's traveling through, heavy rain or hail or water-coated hail, things like that. So we're really going to focus on reflectivity and velocity for the rest of the presentation. So what is reflectivity? Well, from the very beginning, I said that a pulse goes out and it hits a target and it returns power back to the radar. So reflectivity is the measured return power back to the radar from a target. Now that target does not have to be a meteorological target. It can be any target that it hits. If it is a meteorological target, we infer the intensity from the power return. Basically, the more power that it returns, the heavier the rain or the bigger the hail that it's falling through is what we infer. Reflectivity comes in different colors. You'll see different websites have different presentations of reflectivity, different apps. The units are in decibels of Z, and it's denoted with Z. So that's what reflectivity is. And the scale ranges anywhere from about -35 dBz to +85 dBz. So how do we interrogate reflectivity? So you can see the picture here. It's got a big old hook echo, big storm, big supercell storm here. This was the Wiley hailstorm that chunked the baseball to softball size hail through many people's roofs. And this is what the reflectivity looked like for that storm. So basically what you absolutely want to know when you're looking at reflectivity is, what does your scale look like? So when you are down here on this color scale in the blues and these light grays here, generally anything below about 15 dBz is very, very light, whether it be light rain, drizzle. Then you get up to about 20 dBz, 30, 35, and that's typically your light rain. 40 to 50 is typically your moderate to heavy rain. Above 50, we start getting into the really heavy rain. You can see this on the forward flank of the storm here. It's usually where we get some really heavy rain. And then you get up above 65 dBz, and it's usually all hail at that point. By the time you get up that high in the return power, there's ice, it's hail, extremely heavy rain, water-coated hail, returns a lot of power back to the radar. Now, I've got some asterisks next to light and moderate here on the lower end of the scale here. And it's because you can't always just assume that these lighter reflectivities are lighter precipitation. In fact, today, in an environment like today, where we have a deep tropical air mass in place, you can get really, really heavy rainfall rates out of reflectivity that doesn't look all that impressive. So in this image here, we've got a nasty little bow echo that was moving through the southern part of the Metroplex. But on the north end of this, we had a little storm that kind of sat stationary there. And that little storm produced over 4 inches of rain in 90 minutes. out of reflectivity that was typically in the 40 to 50 dBz range. We were in a really warm, moist air mass, and we call these warm core rains. The rain that falls, the drops are usually really, really small. There's just a ton of them, but those small drops don't return a tremendous amount of power back to the radar. So remember, reflectivity is a measure of how much power is coming back to the radar. So if it's not returning that much power back to the radar, the reflectivity won't be that high, but the rainfall rates may be very, very heavy. If you've ever seen a hurricane on radar, rarely will you see reflectivity that is in the bright reds or anything like that. But if you've ever been in the rain from a tropical system, it's just relentless. But the reflectivity is usually anywhere from 30 to 40 dBz over the most of that storm. So that's why I gotta say you got to be careful a little bit, especially in heavy rain events with the reflectivity. But in a general sense, the higher up on the scale that you go, the heavier the precipitation is going to be. So what do we look for when we're looking at reflectivity? You're going to see a lot of 4 panels in this presentation, and it's because I like to take advantage of seeing multiple elevation angles all at once. It's another advantage of doing the volumetric scanning. So here, typically the convention with 4 panels is your lowest elevation angle will be your top left one, and then you will go clockwise up to higher elevations. So you go, around to the right and look up in the storm. So in this 4 panel here, down at 0.5, we've got what looks to be a hook echo, nice big supercell looking storm at 4 degrees in elevation. Still kind of have that same structure here, but now I've got this little donut hole looking little feature right here. That's called a bounded weak echo legion, and it's indicative of a very strong updraft. So here's our updraft region. If any of you took the basic or advanced Skywarn presentations, the webinars that they did earlier, they went over a lot of this, but your updraft region is right here. And that updraft is really, really strong. So you can actually see it in the mid-levels there with a little donut hole. Let's continue looking up here, and even at 10 degrees, you kind of see that same little feature. Very, very strong updraft. And then at 15 degrees, we see this little spike coming out of the back of the storm. You can actually see it at 10 degrees as well. This is called a 3-body scatter spike, and that's basically an indication that there's hail in the storm. And these little spikes like this will always be down radial of the core of your storm. So you can see the core of highest reflectivity is right in here in these deep reds and purples, and then your 3-body scattering is going to come down radial of that. So just by looking at these 4 panels here, I can make the assumption that this is probably a well-organized supercell thunderstorm. It's got really good structure here. It's got a very intense updraft, and it does have hail in it. Now, I don't know what size the hail is. I need to do a little more environmental assessment. But given the structure of the storm, it's a good bet that there's some large hail in that as well. You can also make out a little boundary here. So all kinds of little features show up in the reflectivity. Now, if you are in this location right here, where the red dot is, basically at the end of the arrow tip on the 0.5, you go, wow, it's not really raining at my area, but it's coming. Well, that's true, but look at the reflectivity core that's being held aloft by that updraft. And I'll go ahead and tell you, we'll go over this storm a little bit more, but this was the big hailstorm on April 28th, I believe it was, that went across northern Tarrant County and dumped all the baseball-sized hail and Keller, and it kind of went up toward just north of the airport. But that updraft was holding all that hail above this area right here. So another advantage to looking at multiple elevation angles. Now, it's important to know your scale. You can use any kind of color scheme that you want. If you've got apps, some of them will have different color schemes. If you've got software like the GR software, you can load your own color schemes in there and do all kinds of cool stuff. I don't care what you do, as long as you know where you are on that color scale. What is your reflectivity value on that color scale? So these two images here are identical. One looks a lot scarier than the other one, but the data is all the same in these storms here. So always reference your color scale, despite the fact that these look very different. Everything is the same. A lot of times you're going to see these scarier looking images. They show up on social media. Sometimes they'll show up on TV. They just look ominous, but the data itself is all the same. Velocity. Let's talk a little bit about velocity. It's the other major product that we'll look at. And again, this is a 4-panel of velocity going clockwise around. We've got the 3 lowest tilts, or actually the 4 lowest tilts here. With velocity, we are measuring radial velocity of target samples. We'll talk a little bit about that. The units are usually in knots, and 1 knot is equal to 1.15 miles per hour. So if you had 10 knots, that would be 11.5 miles per hour. Now, the typical convention for velocity is your greens and your cool colors will be winds blowing toward the radar, and your reds and your warm colors are winds blowing away from the radar. I use a green-red color scheme. You can use any color scheme you want as long as you know which direction is which. There are a lot of folks out there that have a hard time seeing reds and greens, so they modify these to blues and reds or some other variant of color that they can see, as long as you know which way is inbound and which way is outbound. And so what are we looking for in the velocity data? Well, when we're looking for circulations, we want to see these red and green colors very close to one another, and we'd like to see some vertical continuity with it. So here you can see a green-red couplet down low, and as we go up in elevation, we kind of see the same thing continuing. So we want to see some vertical continuity when we're looking for circulations. The mesocyclone, that's ultimately what we're trying to sample when we've got supercell thunderstorms or we're worried about tornadoes or anything like that. A mesocyclone is a cyclonically rotating vortex. It's got a diameter usually between anywhere from 2 to 6 miles in width. They extend through a deep part of the storm. Those features will show up in the lowest part of the storms all the way up above 20,000 feet. The area that we're really concerned with prior to tornado formation is usually the level in between, say, 4 and 8 to 10,000 feet. A lot of times we'll see a rapid intensification of the low-level mesocyclone prior to tornado development. And so when the warning forecasters are at the office, a lot of times, you know, you'll hear us say something like, yes, the storm is rotating, it's got rotation in it. A lot of times that rotation is broad and it hasn't really tightened up in that critical layer prior to tornado formation. When it does, that's usually when, you know, we'll issue a tornado warning or something like that. We're going to go through a couple of cases here in a little bit more detail. So what is radial velocity? Radial velocity is the component of your true velocity that is moving directly toward or away from a fixed point. And with weather, we're moving toward or away from the actual radar itself. So in this example, I showed the police officer on the side of the road, and he's, you know, got his laser gun out and shooting it at the cars coming. And On the example here to the left, we've got the officer is actually right in front of the car, and he's shooting the radar down at the car coming at him. Now the car is moving at 80 miles per hour, and he's directly in front of the car, so he's measuring the whole component of his velocity. So his radar is going to indicate 80 miles per hour. Now, if the officer moves off to the side of the road and is at a considerable angle to the road, let's say 25-degree angle here to the road, and your car is moving down the road at 80 miles per hour, and he shoots his radar gun at that 25-degree angle, hits your car, some of that energy goes back. Now, because he's at that angle, he's not actually sampling your whole velocity. He's only sampling a portion of that true velocity. And at 25 degrees, when he hits the car at that range, his radar is going to indicate 73 miles per hour. So your radial velocity in this case is 73 miles per hour, even though the real velocity is 80 miles per hour. So now that becomes important when we're looking at any kind of velocity image here. And here's an example of what I'm talking about. In this example, I just give you the velocity data. Nothing else. You know where the radar is. It's right here in the center. And if you remember, the greens are blowing toward the radar, reds are away from the radar. And just by looking at this, I can infer that we have a southeast wind. Here's our greens and here's our reds. So that makes sense. This area here, this gray area, and you can see this gray area extends all the way back up here. We got this little gray all the way around. This is called the zero isodop. And it goes, like I said, all the way around here, anywhere this little gray line is. That is where the wind is perpendicular to the radar beam. Now on the Nexrad radar, the radar spins around clockwise. So let's start from the top here, and let's scan our radar around, and we get to about 45 degrees here. And the radar sends out a pulse, and it goes out, then it hits a target and comes back. But we already said that the actual wind is out of the southeast. So we can infer that the wind is southeast, southeast, southeast. And that pulse that goes out here, now the wind is perpendicular to it right here. So if you're perpendicular to the true velocity, the radar is going to say, I don't sample anything. Well, it samples something, but it says the velocity is 0. So this area here where this red-green meets on this gray line, like I said, it's called the zero isodop. That's where the velocity is 0. The radial velocity is 0. But the actual true velocity is not 0. We know the wind is still blowing here. It's just that the radar is not directly sampling it. We could probably estimate that the wind is blowing about the same speed as it is here near the radar, probably everywhere across here. Now that makes it interesting because let's say we have a squall line has really, really strong winds in it, and your squall line is approaching the radar and it looks really, really good. It's like, wow, there's a lot of strong wind. And then it gets lined up right over the radar like this, and then the radar beam goes around and shoots off to the north, and it says, hey, I've got 0 velocity here. Well, we know that that's not true. We got this big squall line moving through. But that's one of the limitations of radial velocity. So takes a little bit of interpretation to know, to make a good estimate of what's going on. Squall lines can be particularly problematic, especially when they're lined up perpendicular to the radar. But let's look at this feature out here. And this looks pretty interesting. Remember, greens are toward the radar. So here we've got southeast winds. And now all of a sudden over here, I've got what appears to be a northwest wind and a southeast wind, really close to one another. Big bright blue colors next to the bright reds. This feature here is obviously an area of rotation, and you can see the strong inbounds wrap all the way around this. So if we were to, say, draw some arrows on here, which way the winds were blowing, we've got our southeast winds, and now all of a sudden we have this feature out here. So this is a very, very strong rotation signal associated with a tornadic supercell. And this is really kind of what makes the Doppler radars really good at tornado detection. Because unlike a squall line where the line itself can be oriented perpendicular to the radar beam, when you have a tornado or an area of circulation that is spinning, there's always a component of that rotation that is moving toward or away from the radar. So it doesn't matter where this circulation is. It can be over here, but if it's spinning, there's always a component moving toward and away from the radar. So Doppler radar is very good at detecting areas of circulation, and particularly very strong areas of circulation associated with tornadoes. That's why these signatures show up so well, and something like a squall line can be a little more problematic to deal with when looking at velocity data. All right, storm relative velocity. I wanted to throw this in here because it is a product that is available to you out there. If you use radar apps, you'll see storm relative velocity sometimes. It's a computed-based product. It uses the base velocity, but it does some computations to it to improve what you're actually seeing in the velocity data. So in this animation here, I show you a cluster of storms that are moving through. They were initially a broken line of severe thunderstorms. This was actually kind of a unique event where the storms kind of transitioned from a more linear cluster into more discrete supercells. It's usually the other way around. But you can see these storms are hauling along at a pretty good pace here. And if you look closely, just east of Metropolis here, there's this little feature that kind of spins up right in there, a little high reflectivity associated with that. So when we look at the base velocity, this is radial velocity product, we can see the strong inbounds. Those storms are moving west to east, and then they get on the other side of the radar, and now they're strong outbound. And then right near Brookport, we see this very, very strong outbound velocity here. This was around 80 miles per hour outbound. And I don't really see a very strong inbound. There is a weak inbound right there. But nonetheless, this is the feature of concern. If you're looking at this in your radial velocity image, this screams, hey, you need to look at me. Something is going on here. But it doesn't show up real well. But when we look at the storm relative velocity product, you can now see that the red-green couplet really stands out right there near Brookport. So the difference between this and this, they look very different, but it's the same data. We just did some calculation to it to make it look better. This was the 4 lowest tilts of this circulation. And as I mentioned, we want to look for vertical continuity to this circulation. And you can see very strong inbound, very strong outbound, nice tight circulation right there. It extends up through multiple elevation angles. We would obviously have a tornado warning out on this. And in fact, this was a tornado that moved through Brookport, Illinois, at 2:20 in the morning. Unfortunately, it hit some mobile homes. There were 3 fatalities, a little over 30 injured. The storm itself was moving 52 miles per hour. So the tornado was moving along the ground that whole time at over 50 miles per hour. So how does storm relative velocity work? So these 2 images, as I mentioned, have the same data in them. But when storms are moving that fast, that storm motion, that 52 miles per hour, is included in the base velocity product. So when you're looking at your radial velocity or base velocity, that 52 miles per hour is in there. And so sometimes in this case, it will mask the inbound velocity on that side. So what storm relative velocity does is it subtracts out that 52 miles per hour, and it shows the actual rotation relative to the storm. So basically it sets the storm motion all to 0, and it shows me the actual rotation in that storm. That's why that little couplet shows up so much better in the storm relative velocity product. Now, if you're an experienced meteorologist who looks at radar data all the time, you know that this is a tornadic circulation just by looking at it. You don't really need the SRM, but this does kind of clean up the product a little bit better. All right, algorithms. I used to give this talk in Skywarn presentations, and I'd harp on the algorithms all the time, because if you've got a radar app or you use the GR software, you have access to all kinds of algorithm data. And the Nexrad Radar will produces a bunch of algorithms, all kinds of cool products to tell you where the rotation is. It'll tell you how big the hail is, how strong the tornado is, but they come with significant limitations. And I used to just really harp on it and say, don't use the algorithms, don't use the algorithms. They can be helpful. They can draw your attention to certain features, but they do come with a significant degree of error a lot of times. And this was a different case, but I wanted to show you an example, kind of an extreme example of how algorithm data can be a little bit misleading. So in this case, we have storm relative velocity at 4 different elevation angles. And again, we look for vertical continuity. We see that here. And you can see very strong inbound, very strong outbound. And it goes up through multiple elevation angles. Also see this little green triangle here on the 0.5 degree slice, which is indicating a tornado vortex. It's an algorithm. It says, hey, I've analyzed the velocity data and this thing is spinning and there's probably a tornado in there. But there are a couple of limitations with this. If you take the little green triangle as gospel and say there's a tornado right there, there can be a significant amount of error to that. First of all, the algorithms usually are usually produced at the end of the volume scan. Some of the newer algorithms are produced on the fly, but a lot of the legacy rotation and tornado algorithms were all produced at the end of the volume scan. So remember, if your volume scan is 4 or 5 minutes long, you can already build in a delay in there to when you're going to see that algorithm data. This was actually a tornado near Evansville, Indiana, and it actually tracked hit this racing facility just north of the river. And this is the interstate here. And unfortunately, there was one area of residence south of the interstate, happened to be a mobile home park, that the tornado tracked from this racing facility across this mobile home park and then did some damage over on the east side of town. There were 20 fatalities in this mobile home park. This was another storm. This storm was moving at 62 miles per hour. And because of that fast motion, there is even even when you look up higher in elevation, that storm is moving along. So I'm going to go back here, just back to this SRM page. And if you look at the 0.5 degree slice where that rotation is, the storm is moving so fast that by the time it scanned the 1.5 degree slice, this storm is already, 3/4 of a mile away from where it was at 0.5. So by the time you see this data, that tornado is already downstream of there. So you got to keep that in mind. The tornado vortex that was indicated by the algorithm showed up here at 2:01 a.m. The center of the rotation on radar was here, but the actual tornado was off to the north of the center of the rotation, almost 4 miles displaced from where the tornado algorithm put the symbol. So my main point here is be very careful with algorithms. Use them to maybe draw your attention to a storm, but analyze the base data. Go look at that velocity data. Go look at the reflectivity. See how fast that storm is moving, and don't just rely real heavily on the algorithms. All right, another derived product that we'll talk about other than the algorithms is composite reflectivity. This is actually one of my favorite products. And I think that if you've ever looked at your radar app, if they have composite reflectivity, I use Radar Scope. If you use Radar Scope, composite reflectivity is available on there. And we'll talk a little bit about it here. So composite reflectivity, remember, we talked about the volume scan strategy, and that all comes into play with composite reflectivity. On the image on the left here, I've got 0.5 degree reflectivity. So this is your base reflectivity, and I can see this cluster of storms off to the west through Parker County and Hood County. And then I see these little guys here, one in Johnson County, one in Ellis County. They don't really look all that impressive on the 0.5 degree reflectivity. Certainly not as impressive as these guys out here. But they do have a pretty interesting little structure to them. They look a little, they've got little hooks on them. These are little mini hooks, little mini looking, something that we need to look at for sure. So something else that you notice about these storms on the 0.5 is they're out ahead of this main little cluster of storms. These guys are kind of by themselves. We always worry about little storms that are by themselves like this, especially if they've got a little interesting structure to them like this. Now, when we look at the composite reflectivity, I noticed that particularly the one in Johnson County is pretty impressive looking, a big old core of reflectivity on it. The one in Ellis County, not quite as strong, but also has a nice reflectivity core on it as well. So what is composite reflectivity? What am I seeing here? Why does it look different than the 0.5? Composite reflectivity will take the maximum reflectivity from every elevation angle that is scanned and mashes it down into one reflectivity product. And so what it allows you to do is quickly assess that really high reflectivity that's being held up aloft by your updraft. So I can look at the composite reflectivity image and say, whoa, that storm in Johnson County has a massive updraft on it, because somewhere in that storm, now it doesn't tell you what angle it is, but somewhere in the volume scan, there was really high reflectivity being held up that you don't see at 0.5. So it allows you to quickly assess that real high reflectivity. The problem with composite reflectivity, a couple of them, are low-level features like these hooks and any kind of boundary are almost always going to be masked because it's a mashed composite product. So you're not going to really see hook echoes or anything like that in your composite reflectivity. The other downside to composite reflectivity is it's only produced at the end of the volume scan. So you have to wait until all of those elevation angles are scanned before the product shows up. But it is an excellent tool to use, particularly in the summertime when you have these pulse storms go up really quick and then collapse, a lot of wind. They're excellent for pulse summertime environments. I'll show you a case here in just a minute. The other cool thing with composite reflectivity is if you've ever been those late afternoons and evenings where you have a big old line of storms that'll move through, or we have storms way off to our west, and then all of a sudden you start hearing thunder and you get these bolts out of the blue, go look at your composite reflectivity. you see how far this reflectivity extends off of these storms in the composite reflectivity? So that's telling you that there is precipitation up aloft in these storms that you don't actually see at 0.5. A lot of times that's where your ice is, and you can get bolts of lightning that'll drop out of this that you'll see show up in the composite reflectivity. So composite reflectivity is a really useful derived product that you can look at. This is an example of pulse summertime thunderstorms. They're notorious wind producers in the summertime. The image off to the left here is our 0.5 reflectivity, and you can see I don't really see a whole lot there that looks impressive at 0.5. But when I look at the composite reflectivity, I see 4 distinct updrafts with pretty high reflectivity in those storms. And summertime thunderstorms are notorious for developing really, really strong updrafts. There's usually not very much wind shear, so you get all of that precipitation held up, and then it just comes crashing down. And you'll get your microburst environments, you'll get 70, 80 mile per hour winds, and then it'll be done. Composite reflectivity is an excellent situational awareness tool to keep an eye on during those kinds of environments. So we see these really high reflectivity cores here, and if we were to actually go and analyze the individual elevations, those high reflectivity cores were coming from around 21,000 feet in those storms. You can see a little spike off of the back of here. There was actually some ice and some small hail in this one. And I think 2 of these actually produced severe wind gusts. So composite reflectivity, again, I'll throw a shout out to that. If you have radar scope or something like that, check it out, especially as we get into the summertime. It's a pretty cool little product to look at. So that is kind of an assessment of the base and derived products. And the latter half of this presentation, we are going to go through some actual radar analysis and some warning decision process, kind of walk you through some of the steps of things that we're looking at in the office, and go through the warning decision process. I will, again, just take a little bit of a break here, and David, if there's any other questions or anything we need to talk about or fix here, we can go ahead and do that.
Oh, could you repeat that one more time?
I said we just we're at just a little bit of a breaking point, so I didn't know if we had any other questions or anything that we needed to discuss here.
You know, the questions, no, we've been answering the questions. I think the biggest question that people have is actually, are we going to record this presentation, and are the slides going to be available? I know the plan is we are recording this presentation now, and then we want to upload it. And we might do another talk either in a month or 2, or maybe before the fall time. But at some point, we will record and upload this presentation.
Yeah, I don't think there's anything in here that's copyrighted or anything like that, so we can definitely share the slides. Yeah, I mean, if you've been to before COVID and all the shutdowns and all that, a lot of this presentation in some form or another was given at a lot of the Skywarn talks, but this kind of opens it up to a little bit of a broader audience, maybe somebody who wasn't able to go to one of the Skywarns or anything. And we do these a lot, so yeah, I can, or one of us can definitely go through this again.
That's it as far as the common questions we got. Right now, let's see. People are asking questions. What I'm doing, I'm replying to individuals instead of just replying to everybody. If there ever was a common question, then I would reply to everybody, but let's see. I'm just reading through the questions here. Let's see, so this is a question. So after sunset, what causes the high amount of scatter that would seem to indicate rain? Although if you go higher in the degree scan, you don't see anything of note. So that question, what you're doing, you're actually asking about ground clutter. So what happens is the radar beam, when you get into these overnight situations, the radar beam actually gets bended back down towards the earth. And as it gets bended back down towards the earth, the bottom side of the scan, so remember Jason talked about how it's a volume, it's not a laser beam. So the bottom part of that volume is actually detecting the ground. So what looks like rain because you're getting these high returns back, but it's actually detecting parts of the ground. So that's ground clutter, and that happens overnight, and then you'll see it go away during the day as basically atmosphere heats up, and you lose that bending of the radar beam back down towards the ground. Somebody asked, can you explain dry air mode function and the advantages of being in that mode? Yeah, so that's, well, basically whenever we don't have storms, we don't need to have the radar spinning as fast as we do whenever we do have storms. So that's one of the things. I'll turn on my webcam so you can see me answering the question. So that's one of the reasons why we have, it's called a clear air mode. We have that basically just to save wear and tear on the radar. Somebody asked a question earlier today about one of the limitations or what causes the radar to go down most of the time, and it's actually maintenance. So doing routine maintenance to make sure that it stays up and spinning. I'm not sure if people realize that it's spinning 24/7. So even if we haven't had rain for a couple weeks, the radar is still spinning 24/7, so it never stops. So we take it down a lot to do some preventative maintenance to keep it going whenever the weather is active on days like today. But clear air mode, that's one of the reasons, just to slow it down, less wear and tear. The other thing is that it's actually more sensitive. So if we don't have storms outside, then we want to be able to detect a little bit more sensitive the air currents or things like that. So we'll put it in clear air mode so we can detect those. The other time that we use it is during really light precipitation. So if we have drizzle, we'll put it in clear air mode because it can detect drizzle when those really long pulses that Jason talked about earlier in the presentation. And then also for snow, we can detect snow a lot easier with those clear air modes, which is counterintuitive because it's clear air, but it can detect some of that lighter precip a little bit better. Somebody asked about becoming a storm spotter. You can take the Skywarn courses, and I don't think we have any more for this year, but you can come back next year and take the Skywarn course next year. And let's see. How accurate are the accumulation scans? That really depends on the environment. Some days they're pretty accurate. We try to make them as accurate as possible. There's different algorithms. We can change some of the variables around depending on the environment. Sometimes they're pretty good and sometimes they're pretty bad. It just depends on basically each day. Could be a little bit different. William, you asked about, will you be discussing a debris ball? I think debris will come up later on in the presentation. Let's see, how do we know what mode the radar site is in? On a lot of the apps, they'll tell you what mode it's in. I don't know, there's a lot of people asking about radar scope, and I think on radar scope, if you have that on the top of the screen, it'll tell you what mode it's in. And then a lot of other apps, they'll tell you what mode it's in. If you happen to be looking at an app that's basically a flat map across like the state of Texas, then it's probably not going to tell you the mode, because that's usually what they do. They'll stitch together all the different radars around the area, put that onto one image so it looks pretty. So you're not going to be able to see what mode it's in. I think that's pretty much all the good questions that we got right now. That I'll type back to a lot of the other questions that we have. A lot of them are just asking for software. What's our favorite software and things like that. As far as favorite softwares or software recommend, we don't really recommend any software, but what I can do, I can tell you what we use. I know in the office we use Radar Scope to send out tweets and Facebook posts and things like that, just because it's easier to put it on the iPad and then send it out that way. I know on my personal phone I have Radar Scope, and I use the GR Analyst software you can see on the computer behind me. So even at work, I have my workstation on AWIPS where I can see basically a direct feed into the radars, but we still use the GR Analyst program. So that's been a lot of the questions.
Sounds good. Thank you, David, for answering a lot of those. Yeah, similar to David, I use Radar Scope on my phone. I've got the GR software on my laptop as well. I know with the GR software, there's a lot of archive data, so you can go back and look at cases as well. Okay, David, thank you so much for answering those. Yes, we will actually talk a little bit about three signatures coming up. And I wanted to also mention something about radar uptime. David kind of touched on that too. Believe the last analysis we got that unscheduled outages or basically radar uptime is above 98% outside of maintenance. So we do take it down for maintenance, but basically meaning unscheduled. So it's above 98%. I think it's about 96% for Granger. They've come up quite a bit. They still have some issues down there with that one, but all in all, radar uptime, especially for the Nexrad network as a whole. Remember, these radars are old. The systems themselves, a lot of them, date back to the mid 90s. And like David was saying, they are constantly in operation. We don't ever shut them down. So still, probably I would go as far as saying it's the best overall network in the world as far as radar surveillance, across the country. All right, so let's go ahead and start talking about some radar analysis and the warning decision process. What we do, David and Jennifer and a few others are at work tonight. They're at the office. They're watching the rains out there this evening. So anytime there's active weather, they will be continuously monitoring the radar and making warning decisions or non-decisions. And we're going to go through a little bit of that here in the next couple of cases. So we all remember, or most of us probably remember, especially if you live in the Metroplex, the Dallas County tornadoes back in October of 2019. It was a particularly busy night at work. Kind of touched on this in several different talks. I know some of it came up in the Advanced Skywarn earlier this season. I've given a couple of presentations on this particular event by itself. But this was a classic tornadic supercell, case that wound up producing a pretty significant tornado over in Dallas. One of the most important things that we do as meteorologists is an environmental analysis. We don't just go into the office, plop down in front of the radar and start issuing warnings. If you don't have a good understanding of the environment itself, it makes it really hard to conceptualize what you're seeing on radar. Does it make sense? Why am I seeing something like this when you may be expecting something else? So everybody that goes in and sits down in front of the radar usually does some sort of environmental analysis. So we're going to go through that briefly with this case, show you some upper air maps. This would be maps of the jet stream on that particular day. This was in the morning. We have a jet stream over the southern plains. Not a particularly strong one, but jet stream is there. By evening, though, the image on the right here, we notice that we've got this coupled jet stream structure here. We've got our jet to the west here that's going through the central plains, and we've got this subtropical jet that's streaming through central Texas. Maybe a little difficult to make this out, but you can kind of see the spreading of the winds, these wind barbs across the southern plains. So that's usually pretty favorable for storm development. That spreading of the winds like that is good for the upper parts of thunderstorms when they're developing. We'll go down a little bit lower into the atmosphere. This is around 18,000 feet. And we can see, if you've ever read any of our discussions or sometimes we'll mention it in tweets about upper level disturbances, this would be one moving through the Rockies here in the morning. By evening, it has moved into the plains, is a little bit deeper. Again, we kind of see the spreading of the winds across much of the southern plains. Those winds have increased. And then at the surface, we usually will do a surface analysis. We had an area of low pressure in northwest Oklahoma. We had a classic dry line, cold front, warm front. And then here's our surface moisture. These are dew point lines. This is a 60-degree dew point, 70-degree dew points, which is very humid. Good low-level moisture in the environment at 6 o'clock. By 7 o'clock, that moisture continues to advance to the north. This is 8 o'clock. Our cold front is starting to overtake our dry line. And then this is 9 o'clock. You can see these 70-degree dew points have made it all the way into the metroplex around 9 o'clock in the evening. Still ahead of the cold front and the dry line. We're still warm. It's about 80 degrees with 70-degree dew points, so a warm, humid night. And we were expecting thunderstorms during the evening, overnight hours, particularly along the cold front. It was kind of a slam dunk case as far as the squall line that we were expected, or the cold front to develop. There was a low chance for isolated storms to develop ahead of that cold front in the warm sector where the moisture was greatest. But we weren't super confident in that scenario. We knew it was possible, but again, that makes it difficult to message. If you follow our Twitter or you see these graphics that are posted, I know there's a lot of text on here. We won't read it all. We'll just kind of go through it. But a lot of times it's really difficult to put out a graphic or a tweet that explains all the possibilities without having a bunch of text on it, like you see here. And inevitably, it doesn't matter what you put out. The clear message still kind of gets lost. So the clear message on this particular day, what we were trying to point out to our partners, emergency managers, the media, and the public was, we expect severe weather, primarily along the cold front overnight. There is a low chance that you could have some severe weather ahead of the cold front, and if we did, they could contain all modes of severe weather: large hail, tornadoes, damaging winds, things like that. That's hard to message in a graphic without getting too wordy, and this is a fairly wordy graphic. But basically, we highlighted a pretty large area where we thought severe weather would occur, and then we highlighted a yellow outlined area. And we put a little text on here that said greatest threat for severe storms during the evening hours in this area. Now, we did get storms ahead of the front, as we know, but this was a graphic that was produced at 6:40 in the morning, so about 15 hours before the tornado occurred. And those storms did develop, but we were about 2 rows of counties off in our placement. Thought they'd be a little bit closer to the Red River. We said tornado threat, generally low. We don't really expect tornadoes along the cold front itself, but there was a brief window early to mid-evening with initial storms that developed close to the Red River. And again, we thought they would be a little bit farther to the north. So that was the message. We knew that it was possible, but low confidence in the isolated stuff, much higher confidence in the severe weather along the cold front. 5:30 in the evening, I happened to work this event, and it was a Sunday evening, and it was fairly quiet. If you remember, the Cowboys were in town. They had a primetime game. Everybody was excited watching that. It was a pretty quiet night at work, all things considered. We had enhanced risk out. Usually the phones are ringing off the hook. The chat is going crazy. And these events usually, take multiple people to work. We'd actually staffed pretty heavily overnight because we knew we would have severe weather during the overnight hours. So this is what it looked like at 5:30. This is the radar. It's pretty quiet. Got a couple of storms out in the warm sector across Anderson County and then Cherokee County, which is in Shreveport's area. So not much going on. The first hour and a half of work was pretty quiet. This is our chat log. We have a chat system and we talk a lot with the media and emergency managers so that we can push information out. We got a question from the media and they were asking if the cap was still holding. And I responded and said, yeah, cap is holding, 1 minute satellite imagery. I'll show you that here in a minute. It doesn't show any substantial development. We still had some cap remaining. And then they said, well, I just saw the storms over Palestine, wanted to make sure I wasn't missing anything. Now, the cap was nearly gone across southeast Texas, but that wasn't really where the forcing was. So most of that stuff was not going to be our primary area of concern. The Storm Prediction Center did issue a mesoscale discussion. Watch probability was 40%. That was for the southeast stuff. And I mentioned that in the chat that was for the stuff that was kind of out of our area. So watch probability 40%. This was the 1 minute satellite imagery of that evening from about 4 o'clock to 5:30. And you can see quite a few things on here. First, we see these little horizontal roll clouds, these little billow clouds here streaming through the metroplex. So we've got some lift, but it's not really strong vertical development. It's bumping up against a cap there. So we don't really see much development here. We do see the little storms developing in the southeast here. This area right through here is primarily uncapped. Then we look out to the west, and this was where we were, we initially thought Red River, and then we start turning our attention to this when we see these cumulus fields develop out during peak heating. And if you watch this little guy out here, we did get one little convective attempt, and it never made it. That tells us that it's running into some dry air or the cap. So at 5 o'clock, we still see these cloud street features. Our cumulus field is off to the west. We had one convective attempt that failed, and you can see its mid-level debris went blowing off. Then by 5:30, this diminishing cumulus field, everything kind of suggested at this point that, okay, our window is closing on development ahead of the cold front. That happens a lot during the spring. We got a little cap, and we're watching, and it just doesn't happen. And I really hope that this portion of the presentation kind of gives you an idea of how the forecast rapidly changes. You get up, you look at your weather service, not app, because we don't have an app, but if you go to the web page and you say, wow, they said, 60% chance of rain and it's sunny and this and that. A lot of times that forecast can rapidly change, and this changes within about 90 minutes from going from this point at 5:30 in the evening to where looks like that window is closing. We're going to have to wait until overnight to, we've got a problem. So a little bit later, this is about 6:15. We had one of our aviation partners chat us and said that they were working the remains of the air show at Alliance, and they're watching some cells to the southwest. We actually started getting some development off to the southwest. What's your thoughts? And my partner that night at work, Mr. Godwin, responds and says, we're going to have to keep an eye on them. There's still some cap. They're going to be fighting. Main show will probably be overnight. That's what it was looking like. Now, this is at 6:17. Now, we have launched the weather balloon, and at 6:17, it is probably going through that capping layer right now, at this point. So we're starting to get the data in, and we're going to sample that cap. This is what the radar looked like at 6:18. We've got some showers out there, little baby storms starting to develop off the southwest of Stephenville. Remember, let's take advantage of those volume scans and look up. And I don't see any healthy cores at 5 degrees. So we've got some little showers developing. Now, these storms struggled for the first half hour to 45 minutes. They would, if you remember that satellite image where that attempt went up and then it failed, kind of saw that in the radar data too with this stuff initially. The sounding comes in. This is the Fort Worth sounding. Now, the whole sounding usually takes a couple of hours. but we at least got the low-level part of the data in, and we could see this cap was still here. That's a pretty respectable cap at this point. And in fact, if you take a mixed layer parcel, if you basically take air in the lowest, I don't know, 500 feet or so of the atmosphere, because it's turbulent, there's wind blowing around, and you lift that, there was actually a pretty significant cap still in place over Fort Worth. And that's important. Remember, we launched the balloons in Fort Worth. This image off to the right here, this photograph, is kind of a plot of wind shear in the atmosphere. And what we're looking for tornadoes would be a photograph that's a large curved photograph that indicates a lot of turning of the low-level winds and strong low-level winds. So we got a lot of speed shear and directional shear. And we do see some of that. There is some curving of the photograph in the lowest 3 kilometers here of the atmosphere. And then the photograph gets really straight. So we know that there's some low-level shear. And this photograph will initially favor, the wind shear profile will initially favor supercells with the potential for them to split. And the splitting comes from the mid levels and upper levels of the storm, this long straight photograph here. The wind shear is fairly unidirectional. And so that's going to favor splitting supercells. And that's initially what we see. Now, so we get this data in, this sounding, this photograph comes in around 620 or so, not the whole thing, but the lower levels of it does. So we see that there's a little cap, but then about 20 minutes later, around 6:40 in the evening, now we start to see a little more robust activity on radar. And again, these are the same 4 elevation angles that I showed you earlier, 0, 0.5, 0.9, 1.3, and then the 5-degree slice. And what you'll notice now how the reflectivity is significantly higher with the cell in Parker County. We've got some pretty high, getting up above 65 dBz. But notice at 5 degrees here, you notice this little kind of donut hole thing here. Now, I mentioned earlier that this was a bounded weak echo region. Again, further analysis will tell you, no, that's not what's going on here. This is actually the storm updraft splitting. And this storm is going to split into a left-moving supercell and a right-moving supercell. So that's kind of what's going on here at 5 degrees. So this is getting concerning now, because not only do we have development, but we are starting to see that splitting structure. Conceptually in your mind, you're saying, okay, this is it. Now it's going. The cap that we had in Fort Worth has clearly been breached out to the west, and it's going to tap into all that instability, and things are going to start to take off. Now watch the timeline here. This is 6:37. There's a string of events that happens here really quickly. At 6:28, SPC, when they saw that initial development, or when they saw that development looking a little more robust, they issued a mesoscale discussion. And they said, watch probability 40%. So at 6:28, now this is not the same one that was for the Southeast. This is for us, 40% probability. At 6:38, we say we're watching that cluster of storms. They've struggled a little bit over the last hour. Fort Worth sounding still shows some cap. The cell south of Mineral Wells is the strongest and may be undergoing a split. It was undergoing a split at the time. We'll monitor this closely. 4 minutes later, we issued a significant weather advisory for Parker County for hail. 4 minutes later, about to issue a severe thunderstorm warning for Parker County. 1 minute later, severe thunderstorm warning goes out. Another 5 minutes, we're on a conference call with SPC, watch coming shortly. And then at 6:55, they issued a tornado watch, or we discussed the tornado watch, and then it went out at 6:58. So in a matter of 30 minutes there, we went from watch probability 40% to me saying that there's still some cap. Is this really going to take off? We're looking at this split to significant weather advisory, severe thunderstorm warning, and now the event is underway. So even in that short amount of time, there was still considerable uncertainty as to whether it was really going to take off. And then we all know what happened that night. It did. It was only a couple of storms though. But it only takes one to be a memorable event. So our split, our Parker County storm did actually split. This is the left split up here, and this is the right split here just south of Weatherford. We've got a couple other storms off to the south and east. Our left mover went on, it was moving around 60 miles an hour, went all the way up through Wise County into Cook County and produced golf ball size hail all the way up into southern Oklahoma. And then our right mover kind of had some initial storm interaction there, kind of just chugged along. We had a warning out, and then really got its act together as we went over, as it went over into Dallas County. We do get aircraft soundings in from some of the airplanes that fly into DFW and Love Field. This was an aircraft sounding that came into Love Field at 6:30 in the evening, and you can see on this one that there's still a pretty decent cap associated with it. So that kind of verifies what we saw on the Fort Worth sounding, that yes, the Metroplex still had some capping issues that we were dealing with. The hodograph looks very similar, long straight hodograph supporting splitting supercells. Now, I'm going to go back here. This is at 6:29. Now look at what happens just 2 hours later. The cap is gone. Obviously, our storms are already underway. But look at the low-level wind field here. Now we've got some significant curvature to the low-level winds. Our hodograph, instead of being that long and straight, is now this large looping hodograph here, which is indicative of very strong low-level wind shear and turning of the winds and fairly strong winds. This is the result of an increasing, a strengthening low-level jet, and it really amplified the low-level wind shear profile and made the environment much more suitable for tornadic supercells as opposed to just ordinary splitting supercells favoring mainly hail. And we know that that's what happened. This was at 8:50 in the evening, and you can see the nice structure to the storm, big hook starting to take shape. Now we did have those storms to the south that were kind of interacting a little bit with this. This is at 8:58, and the tornado is touching down right at this point, just west of I-35. Touches down here and then tracks south of 635 across northern Dallas here. Here's our velocity product, a nice tight inbound, outbound couplet at 0.5. I didn't show the 0.9, but here's 1.3. So it's got good vertical continuity, good structure to it. The environment has become incredibly favorable for tornadoes. This is a few minutes later, and you can see the tight inbound, outbound couplet associated with the tornadic circulation. And this is, as it's continuing, I believe it was about to cross the tollway here. Somebody was asking about the debris signatures, and we're going to talk a little bit more about it here coming up. But this, the tornado debris signature has something that's become really popular. Everybody has probably heard of it. It is associated with the dual pole variables that became available over the last decade. And where you will see the tornado debris signature show up is in the correlation coefficient. We'll talk a little bit more about that later on. But at 0.5, we see this nice hook echo here. We see our strong inbound, outbound couplet, vertical continuity to it. And then we also see this drop off in correlation coefficient. Now this is at 1.3 degrees. So I want to look at my 1.3 degree velocity. And they must be co-located. If they are not co-located, then it's not a tornado debris signature. That has to be co-located. So you need all of these features to line up in the same spot for it to be a tornado debris signature. Now, prior to the dual pole variables being available to us, we would only have the reflectivity. And we could still infer that there was debris occurring with this signature and reflectivity. If you notice this little bright area of reflectivity, real high reflectivity, right there where that circulation is, this is debris showing up in the reflectivity. And so that used to be called a debris ball signature. But now with the correlation coefficient, we've termed it a tornadic debris signature. So that's what it looks like, and that's what it looked like on the Dallas tornado. So keep in mind that, and Weather Service meteorologists always have to keep this in mind, that the environment is always changing, and uncertainties persisted all the way up until that event was unfolding. And so if you didn't stay on top of that, you know, things could have gotten out of hand really, really quickly. You know, we went from not sure if we're actually going to see storms to full-on supercells and tornado watch. And then again, this storm ramped up very, very quickly as that environment became very, very favorable. Okay, now we're going to talk about the Tarrant County tornado warning and large hail event that occurred just a couple of weeks ago. This was on April 28th. This was another event that I had the pleasure of working, and this one started out again as an event that we were expecting severe weather, but the environment wasn't quite as favorable for tornadoes on this day. We're expecting primarily large hail and damaging winds, and we were tracking a severe thunderstorm that had developed off to the west of Mineral Wells. It's moving across Parker County, and this is what it looked like around 7:45 in the evening as it's approaching Tarrant County. And again, let's look at our multiple elevation angles. These are the four lowest, and I can see what looks like just a cluster of, or at least one big thunderstorm here moving through Parker County. When I look at the velocity data, there are a couple of little areas of concern. At 0.5 and 0.9, I see some fairly bright greens. These happen to line up with about 50 knots on radar. So it looked like this storm had some severe wind in it as it was moving across Parker County. I don't notice any real strong red outbounds or anything like that that has me particularly concerned with rotation. You could argue that there is some rotation here at 1.3. It's very broad. So at this particular time, I'm not overly concerned with a tornado, but we did have severe thunderstorm warnings out. This storm did produce a pretty good swath of wind damage across eastern Parker County. And we went ahead and issued a severe thunderstorm warning for Tarrant County as it was getting close to the county line there. Now, 15 minutes later, as this has moved into Tarrant County, it's 8 o'clock, and I look at the reflectivity structure here, and now I notice a distinct change in the way that storm looked when it was in Parker County to how it looks now. And hopefully you can kind of pick up on this hook-like structure in the reflectivity at 0.5. It actually shows up on all four of these angles. So this storm is starting to get its, I mean, it was already severe, but it's really starting to get its act together now. We've got this more classic supercell look to it. It's getting a pretty well organized rear flank associated with it. We also noticed a little boundary here. And these boundaries are really, really important. This is the rear flank downdraft. And at this particular time, the rear flank downdraft has kind of surged out ahead of the storm just a little bit. Now, there's a couple issues with that. If it surges out too far, and anybody who chases storms knows you'll get a gust of cool outflow air, it's not going to produce a tornado. But if it catches back up to that rear flank downdraft or this boundary here and can ingest it into its updraft, then it can very, very quickly produce a tornado. And so this structure is very concerning, even though at this particular time, it's probably not going to produce a tornado. A few minutes later, the structure actually gets a little bit better. And this boundary now you can kind of make out here is starting to wrap back into this updraft here. And now when I look aloft at 3 degrees, 4 degrees, 6 degrees, now I start to see some rotation that is particularly concerning. Now, remember I said the environment on this day wasn't particularly favorable for tornadoes. And that doesn't mean that it's not going to produce a tornado. The storm itself can alter the environment. There can be environmental changes that go unobserved that you constantly have to be aware of. So I can't just discount this rotation and say it's not going to produce a tornado. I've done my environmental analysis. Can't do that. This is very concerning. So at this point, I've got the tornado warning drawn up. And what I'm doing now is I'm waiting to see if this rotation persists. Because right now, it does not appear to be an imminent tornado threat. But if that rotation persists, then I'm going to issue a tornado warning. And at 8:08, it does persist. And the reflectivity even looks a little better here, a nice well-defined hook. Now the rotation itself, we looked at some tornadic signatures before, and it's not as strong as we saw in those other tornadoes, but it's still there. So is it producing a tornado or not? I don't know. I don't have a spotter on the ground telling me that there's a tornado. All I have is this data in front of me. I know that the environment is not super conducive for tornadoes, but I can't argue with the data in front of me. The storm has gotten a lot better structurally. It does have rotation in that favored low-level mesocyclone region. And it has clearly caught up to whatever boundary was previously put out. The other thing that really triggered the warning decision was the appearance of the reflectivity in the upper levels of the storm. And this is why volumetric scanning is so incredibly important. On this scan, we saw now a bounded weak echo region, and you saw these images earlier, extend up through about 10 degrees. And at 15 degrees in elevation, this massive core being suspended above this area of updraft. What that tells me is that updraft is rapidly strengthening at this time. Now, if I've got rotation there and I stretch that rotation through a rapidly strengthening updraft, I can increase that rotation very, very rapidly. So the warning decision at this point was made with a combination of the low-level rotation that was observed, even though it wasn't that strong, and the very rapid increase in reflectivity aloft, which indicates that the updraft itself is strengthening. So I issued a tornado warning at this time. Again, this is the three-body scatter spike that we talked about a little bit earlier, down radial from that real high reflectivity core. Now, we also have other data sets that we can look at in the Metroplex. We're fortunate that we have terminal Doppler radars and we have the CASA radars. You probably heard a little bit about the CASA radars. We have 7 of them in the Metroplex that we can use to supplement the Nexrad and terminal Doppler data sets. The CASA radars are X-band, 3-centimeter wavelength radars. They have a range of about 20 miles. And because they're X-band, they suffer from significant signal attenuation. So they aren't very useful when it's raining right on top of the radar. But in cases like this, where the storm is approaching the radar and it's got low-level rotation, they provide fantastic resolution images of the reflectivity structure down low and of the velocity data. And I want to thank Maddie Gordon. She's one of our newest meteorologists for getting these images plotted. We took the raw CASA data and plotted it on these maps, and she was a big part of that. You can see here, this is Northwest Loop 820. This is I-35 going north of Fort Worth. This little branch here is US 287, and then this is Business 287 going through Saginaw. The Fort Worth CASA is located off of Boat Club Road there north of Lake Worth. So it's right here. So you can see, you know, this area here is just Tarrant County. So you can see the resolution that the radar has. This is at 8 o'clock, and then this is at 8:08 when the warning decision was made. So not only am I looking at the Fort Worth Nexrad and the terminal Doppler radar, but I've got this CASA radar too that shows this fantastic reflectivity structure going over the northern parts of Lake Worth and Eagle Mountain Lake here. And you can see this thing wrapping all the way around. Now, I filtered out the velocity data just to match up with the reflectivity data here, but there at this time there was no really identifiable couplet down low. Now remember, the radar is right here, so you're only sampling maybe a couple of 100 feet off the ground. So if we saw a couplet right here, that would probably be associated with a tornado. So nothing at this time. This is 2 minutes later at 8:10, and then this is at 8:13. Now the storm is starting to move over the radar here, so let me go back a couple of frames, and now I'm going to go forward a couple. You'll see in the reflectivity structure back here, you'll notice that we start getting some signal loss here. So the X-band radar starts to attenuate pretty significantly. This is at 8:13, and then this is at 8:14 where we have a lot of signal loss now. It's raining pretty heavily on the dome, but you can see this little spiral right here, and I'm going to show you some close-up images of this. But there's our couplet right there at 8:14 in the evening. This is just a close-up of that little couplet there. Now the CASA radars, they vary a little bit. They don't all scan like the Nexrad. The CASA Fort Worth radar scans 1 degree, 2 degrees, and 3 degrees in elevation. And so we're going to go. It'll scan 1 degree, 2 degrees, 3 degrees, and I'm going to show you those sequentially. And we're so close to the radar that there's not much difference between 1 degree and 3 degrees in elevation. So this is at 8:13:07, and you can see the reflectivity structure all wrapped up here. But I don't see a great deal in the velocity data here, maybe a little something right there. That's definitely the circulation. This is correlation coefficient over here. It's a different color scheme than the one that you saw on the Nexrad, but not anything of importance here at this particular time. This is at 8:13:32, so this is about 25 seconds later, and you can see the signature here. Now I start to see a little bit of tightening of this couplet, don't really see a drop-off, a significant drop-off in correlation coefficient here. This is a missing pixel there in the middle. This is at 8:13 and 57 seconds, so another 25 seconds. And you can see the reflectivity hook wrapped around. And here is my couplet. And fortunately, this thing tracked over an open field on the north end of Marine Creek Reservoir. There isn't much out here. But this is the circulation. Again, no noticeable drop-off in correlation coefficient to indicate that there's any kind of debris. This is at 8:14 and 22. This is when the signature looked its strongest, completely wrapped around. And this is our gate-to-gate couplet right here. You know, as a meteorologist who has looked at thousands of radar images, I would argue that there was probably something in that field. I don't really see a drop-off in correlation coefficient. This outbound pixel here was greater than 30 meters per second or 60 knots. So that's about a 70 mile per hour outbound next to these. That's probably about a 20 or 30 mile per hour inbound. So this very likely was some very brief, just little vortex that spun right there across this field. And then you can see another 25 seconds later, the couplet doesn't look as good. And then this is another 25 seconds later, and it's fallen apart. So just in those 2 minutes there, or a minute and a half, you saw this thing wrap up and then fall apart. And I think the tornado warning was out for something like 19 minutes or so. They went out and looked. Nobody reported a tornado, and we could not find any damage. So either there was a nice big wind gust out over that field, or it just never touched down. We were sampling maybe a funnel or something like that. Now, we don't have the luxury of having CASA data everywhere across North Texas. We've got it in the Metroplex, or most parts of the Metroplex. But that data comes in every 25 seconds. So, you know, you're trying to analyze Nexrad data and terminal Doppler data and CASA data, and all of those pieces of information are coming in and go into that warning decision process. And that's just the remote sensing part of it. That's not the public who's on Twitter tweeting at us and telling us what they have, or the spotters that are out and working with the ham radio network to relay their information back to us. All of those pieces of information come back into the office and go into those warning decisions that are made. So that was a case where a tornado warning was issued based on a conceptual model of what was going on with that storm, and it didn't produce a tornado. And I can tell you personally that, you know, a lot of things go into warning decisions to decide to warn or not to warn. We don't just throw warnings out to better be safe than sorry. We need to have some sort of reasoning behind warning people and telling people, hey, you need to take action. This is dangerous. And hopefully that gave you a little bit of insight as to you know what we're looking at in the office. So those are supercells. Things to keep in mind. Supercells, they can produce all kinds of severe weather. That storm was still severe. It went on, tracked across I-35 and then moved into Keller and rocked that area with really large hail, some damaging winds. Never produced a tornado, but if you ask the folks that got clobbered by, you know, baseball-sized hail, it was still a devastating storm. So supercells produce all types of severe weather. Got to know what our environment is capable of doing. We monitor that reflectivity structure and look for hook-shaped echoes. Velocity data, again, look for vertical continuity. And all of those things go into the warning decision process. Elevated supercells, we'll talk a little bit about here in just a few minutes, but usually not accompanied by a tornado threat, but they do have rotating updrafts. I will pause just for a minute here. I know we're going into the third hour of this, and we're on the tail end of this presentation. So if anybody has any questions or anything, David, or you want to talk about anything, we will do that for another minute or two, and I'm going to grab a sip of drink here, and then we'll finish up.
Hey, Jason. No, everything's good on this end. The questions have been coming in, a lot of questions about the CASA radar data and if we can get to it and see it. Unfortunately, we don't own the data like the Weather Service radar, like the 88D data. So it's not up to us if we're going to make it public and things like that. So a lot of that happens behind the scenes where we're not really involved with it. And then let's see, where do you get the sounding data to analyze with Sharpie? So I know that there's an agreement with the ACARs, the AMDAR folks, where we get the data in real time. I know they don't want to publish it out in real time due to security reasons. They don't want people to know exactly where their planes are at all times and getting all that data. So I think they are available after the fact. I think there's like a 15-minute delay. Jason, do you know what the delay is?
Yeah, I don't know exactly what the delay is, but I don't think it's I mean, it may be up to an hour or so, but it's not, you know, terrible.
Yeah, and then if you just Google AMDAR, AMDAR, if you Google that, then that could get you to it's a Java site, and you can download the text files and put them in Sharpie that way. Let's see, websites that have good radar coverage. You could try to use our web page, our new weather radar web page if you wanted to. It's gotten better, but if you still have feedback, there's a feedback option. So if you do have suggestions, please use that feedback form. But other than that, the questions are all cut up, Jason. We did get hit by that supercell, by the way. So there's a lot of homes in my personal neighborhood, and we were one of them that got hit with that hail. And we took shelter for it, and it was awful.
I forgot that was the one. I worked several of them in there, and yeah, that was the one that hit you and a couple other people at work. So bad storm nonetheless. So supercells are pretty nasty. If you get underneath one, you're you know, you'll be impressed by what it can do. All right, let's go ahead and wrap this up. We're going to talk about just a few other topics here. I want to talk about squall lines real quickly. Squall lines are you know, another type of severe weather. It usually brings a lot of damaging winds to us, but oftentimes we do have to worry about embedded tornadoes. And I'll tell you this, you know, with all tornadoes are not created equal. But when we issue tornado warnings and the sirens go off, everybody's typical response is, you know, you see the pictures of the wedges just tearing things up, and a lot of times that's what goes through people's minds when those sirens go off or when a tornado warning is issued. And that's good because it hopefully spurs them to take action. But not all tornadoes are created equal. And squall line tornadoes oftentimes are not nearly as strong, although they can be, as supercell tornadoes. You know, we still want people to take the same action when we issue tornado warnings for squall line tornadoes. So what do tornadoes within squall lines look like? Remember, I told you earlier in the presentation that squall lines can often be difficult to truly assess wind speed and damaging winds because at some point in the line, the radar is going to become perpendicular to which way the wind is blowing. But with tornadoes, even embedded in squall lines, they'll still show up because tornadoes rotate 360 degrees, and there's always a component moving toward or away from the radar. So here is a squall line about 5 years ago that moved through the southern parts of the Metroplex. Again, we're going to do our analysis of reflectivity through the 3 lowest tilts, and then I throw the 10-degree elevation on there just to point out where the strongest updraft is in this storm. And the first thing that I see in this storm is a nice little bowing structure here moving through southern part of Hood County. And we see that through several elevation angles. And we see this really strong updraft just north of Granbury there. So strong squall line looks like a good damaging wind threat. When I look over at the velocity data, I see really strong inbound velocities. This is moving directly toward the radar. So I see 60 to 70 mile an hour winds here in southern Parker County. I see vertical continuity to that. I see a strong updraft here. I also see a couple of other little interesting things. I see these little kinks in the line here. Those are always concerning when we're looking at squall lines, and we're going to see what happens to those. So it's 7:30 in the morning. By 7:35, just 5 minutes later. Now remember, squall lines usually move at a pretty good pace. Now I've got something considerably more interesting. And if you look at these, we saw them in the velocity a few minutes before, but now look at the reflectivity structure. And I've got these little hooks in the line here, these little breaks or these little kinks, and I've got some vertical continuity to them. Now look at my updrafts at 10 degrees. They've gotten a lot stronger. I've got more than one now, even a third one down here. And so these things are getting a little bit better organized. When I look at the velocity data here, now I really need to be concerned. In fact, a tornado warning went out for both of these at this time. You can see that we've not only got these little kinks, but there's a strong green-red little couplet right in both of these. And there's good vertical continuity, very strong inbound velocities associated with these couplets. And excuse me, let me go back here. You can still see our 3 strong updrafts here associated with this. 740, look at the reflectivity structure. That's pretty impressive. And we see these little hooks all along here. Here's a third one down here. And the 2 to the north did actually produce brief tornadoes. This one down here did not. Here's the velocity data. You can see our good swirls to the north. This one was kind of caught in some range folding here. The range folding is this white color. It could be purple on your I use white for range folding just because I like it to kind of yell at me and scream at me. It tells me I've got a problem here. I may need to try and adjust something. But this one actually did not produce anything down here to the south. So that's what squall line tornadoes look like. They're usually very brief. They can be quite strong, but the downside to these is they usually spin up very fast, and there's usually very little lead time on the warning. You know, we try not to overwarn because you'll see little swirls in the lines all the time. But there needs to be good vertical continuity, and they need to be correlated with a strong updraft to really be concerned for tornado development. So squall lines usually develop in highly sheared, unstable environments. Wind is the primary severe threat that we usually see with squall lines, although embedded tornadoes do occur, and occasionally we can get embedded supercells within the line of storms. Those are much more dangerous. They're a little more common in the southeast United States. You'll see lines with embedded supercells, but we do get them here too in the plains. Remember, with lines of storms, radial velocity can be misleading, especially when the squall line is perpendicular to the radar beam. What we're looking for tornadoes are little small breaks or hooks that surge out ahead of the main line. And we're going to finish up here with just a couple of miscellaneous topics here. Those spikes that we talked about, these are called 3-body scatter spikes. You'll see these in supercells all the time. They're these big spikes that shoot out down radial of the strongest core of reflectivity. And here I'm showing you 8 degrees, 12.5 degrees, and 15.5 degrees. And you can see these big spikes that go down radial. That tells you that there is hail present in the storm. And so what happens during a three-body scatter spike? The radar beam shoots out from the radar, and it hits the hail core or the hail. Some of that energy bounces from the hail back down to the ground, and then back up to the hail, and then back to the radar. Sometimes it can bounce multiple times between ground and hail before it ever gets back to the radar. Now remember, all of this happens at the speed of light, but even those fractions of seconds the radar can process, and because it takes longer for that initial pulse to get back to the radar, it thinks it's coming from farther away than it actually is. So that's why you get these spikes down radial. There's actually nothing occurring in Decatur, but it looks like there is, and it's from three-body scattering. So that's what a hail spike or a three-body scatter spike looks like. If you happen to look at dual pole products, you can look at correlation coefficient. Correlation coefficient will be very, very low with hail spikes because it's hitting hail on the ground and all kinds of things in between. So what is correlation coefficient? Correlation coefficient is basically a measure of the variability of the targets that we're hitting. So when we have a uniform meteorological target like all rain or all snow, you're going to get well-behaved scattering with little difference between horizontal and vertical from pulse to pulse. So there's not going to be much change between each pulse if everything is all rain or all snow or all ice or whatever it's hitting. So your correlation coefficient is going to be very high, usually greater than 0.97. When we start getting non-uniform meteorological targets like hail, wet combinations of hail and rain, you get a somewhat more complex scattering. And so correlation coefficient will drop usually between 0.8 and 0.97 or so. We'll see this a lot of times in sleet, where the melting layer is from hail or snow to rain. You'll see this drop off in correlation coefficient. Non-meteorological targets will have a very low correlation coefficient, usually less than 0.8. And that's the result of complex scattering from pulse to pulse. Debris flying through the air, it's nails, it's insulation and pieces of shingles, very complex scattering from pulse to pulse. So it has a very low correlation coefficient. Three-body scattering between the ground and hail is going to be a very, very low correlation coefficient. This is why the tornado debris signature shows up so well in correlation coefficient. And one of the things that we want to check is, one, I have to have precipitation, obviously. We need rotation, and we'd like to have our vertical continuity. Here's our circulation. We see this drop off in correlation coefficient. Now, the key is these absolutely must line up. And if they don't, it's not a tornado debris signature. So this is not a tornado debris signature. This low correlation coefficient is due to this very low reflectivity right here. They're not in the same spot. Close does not count when it comes to the tornado debris signature. So at this time, the warning forecaster cannot say radar confirmed tornado because we don't know if there's actually a tornado occurring at this time. Now, a few minutes later, as this thing moves off to the northeast, we still have our very tight reflectivity, our velocity couplet, good vertical continuity, and now I see this CC drop, and now it is co-located with the velocity signature, and we can confirm now that this is tornado debris occurring with this. So now, even if I didn't have a spotter telling me what was going on, I could issue a statement saying radar confirmed tornado based on this signature. So that's what a tornado debris signature looks like, and that's why we use a correlation coefficient. Non-tornadic supercells, again, these can be pretty nasty storms. They rotate. They have all the look of a classic supercell. In this particular case, this was in Denton County in 2016. This storm was an elevated supercell. If you look at this boundary here that had moved through Denton and Collin counties, this was a cold front that had moved through from the northeast. This boundary over here is associated with this storm. It's outflow off of this storm, and this storm is moving off to the east into Denton County, right where that cold front had moved through. So the Denton observation at the Denton airport at 3 o'clock went from 80 to 72 at 4 o'clock, and our winds went from variable at 5 knots to north-northeast at 17 knots. So nice north wind with this, cooler air. It's 8 degrees cooler. This storm is moving into a more stable surface environment, but the environment above the front is still very unstable. So that's why this storm proceeded as it moves into across eastern Wise into Denton County. We get this nasty looking what appears to be a rotation signature on radar. And I've been preaching to you, look for vertical continuity, and it looks like it's got good vertical continuity here. But this is kind of where expertise comes into play. I can look at this velocity image here and see that something doesn't look right with this. It's kind of blocky, and it doesn't have the classic, what I would call the drop off in velocities. Usually you get a ramp up in velocities where your strongest rotational velocities are would be right in here, and then you would have a drop off in velocities the farther away from the center of that circulation that you went. I don't see that here. It's just kind of blocky and noisy. Here, you do kind of see that. This ramp up, highest velocity is right in the middle. This is at 2 degrees in elevation. You say, but Jason, look, it's got the classic hook. My conceptual model tells me this thing is tightening up and it's going to produce a tornado. I look at correlation coefficient and it's like, wow, there is a debris signature there. I've got to get a tornado warning out on this, but doesn't need a tornado warning. And the one thing that we cannot lose sight of is we just had a cold front go through there. Denton has cooled by 8 degrees and has a northeast wind. A northeast wind at Denton is not inflow into this storm. And so it conceptually now should not make sense. Something doesn't make sense here. And when we look at, we didn't talk about spectrum width here, but spectrum width is a measure of the variability of the velocity data. Spectrum width is very high in these outbound velocities. And that tells me that there's a little problem. I don't know if you can see it, but there's a little red dot also plotted in the center of that black circle. That red dot is in the same location on each of these frames. And that red dot is right about there in the reflectivity. And so the strongest outbounds are way out here. And that's not where they would be in a tornado. They would be over in here somewhere. So this velocity data right here is bad. It's not real at 0.5 degrees. In fact, it's actually a shadow from the 2.4 degree elevation slice. And if you remember from the very beginning part of the presentation where I said that the radar beam itself is a cone, that cone goes out in 3 dimensions. And what you're seeing here is contamination from a side lobe, from the outside of the beam. Remember, the beam doesn't just end where the power drops off by half. power goes all the way around, and some of that power is hitting this high velocity aloft, and the radar thinks it's coming from 0.5 degrees. This is called velocity side lobe contamination, and it can be really problematic in cases like this because it looks real. In fact, the tornado algorithm plots and says, you got a tornado here, you got to do something. And social media was kind of going crazy. This needs a tornado warning on it, ASAP. Impressive looking tornado signature from a storm just north of Dallas, Fort Worth. The problem was this storm was not going to produce a tornado. This was an elevated storm above the cold air. And as soon as the velocity side lobe contamination cleared itself up, you notice we lose the bright red outbounds. And so you have all these strong inbound velocities here. That makes sense. That's where we would see the inbound velocities on the backside of this. This storm was a hail producer, but did not produce a tornado, and it wasn't going to, and we never issued a tornado warning on it. So this is where you have to be careful, you know, with social media posts and things like that, where, you know, expertise is really needed to understand what's going on with the data that you were presented with there. You had to have an understanding of what was going on with the environment. The environment was not capable of producing a tornado in that particular case. Okay, this is the last couple of slides. Warning decision making. We talked about it a little bit throughout the presentation. This was May 16th, just a couple of weeks ago. This is northern Dallas County. We issued a tornado warning. See a pretty small tornado warning from University Park up to the Dallas-Collin County line. Social media was not pleased. Mr. Scott here was not really enthused with our warning decision making this day. I think he thought it was amateur hour at the Weather Service. Must have been inexperienced personnel. He was just not happy with the warning decision making. They pulled the trigger on nothing. We get these kind of comments on Twitter a lot. Warning decision, I like this part, weather is hard. Weather is hard. Warning decision making is hard. It's not something that we just do willy-nilly and say, hey, I'm gonna throw out a tornado warning today. When that send button is pressed, a lot of things go into motion. First, you're warning people and telling them that if they don't do something, they could be injured badly. Second, emergency managers prepare for a response. Do I sound siren? Do I warn people? Am I going to have to prepare for a recovery or a cleanup response? So a lot of things go into motion when those decisions are made. So again, it's not something that we take lightly. This warning decision, the forecaster made this decision not to go into Collin County. We're not going to warn Collin County because our environment really didn't support long track tornadoes. This was a tropical spin up day, and that's exactly what happened here. A brief tropical spin up, touchdown North Dallas, ripped some roofs off, and then dissipated, and there was never a need for a tornado warning farther to the north. So a lot of things go into play when it comes to decision making. I'm going to just see if I can show you this video real quick. And this is what happened. I think I was muted there. This is just a video from a security camera from somebody's house there in North Dallas, and you can see it gets pretty windy, and then this brief tropical funnel, tornado touches down and does a little bit of damage. And so that was it. That was just the brief tornado did some damage there. All in all, it was a good warning decision making, even though some people in that box weren't happy. So hopefully this gave you a little bit better idea of some of the things that we go through at the office when it comes to warning decisions, some of the products that we look at, a little bit better understanding of some of the stuff that you may look at on your apps or online. And that is all I have. We were slated for 3 hours and we wrapped it up in 2.5. So I'll call that a win. I can stay on here for a little while if anybody has any questions, or David, if you want to, if there's anything else that we need to talk about, we will do that here real quick.
Hey, Jason, great presentation. Thank you for putting all this together. It was really good. A lot of the comments that we've gotten were that it's really filled in the gaps with people. So they went to the basic Skywarn, they went to the advanced Skywarn, and this just really brought it all together and really made it a whole educational experience. So thank you for that presentation, Jason. I would have to say that the thing that we got the most feedback on was your Drake meme. So if we could incorporate that a little bit more in the future, that seems to be appreciated.
Yeah, we'll have to do that.
There was a lot of comments about the last few slides you had about the warning decisions and filling in the gaps as far as what all goes into the warning process, that it's not as simple as what a lot of people think. But if anybody else has any other questions, you can type them in. And then Jason, do you have the questions log open?
Yeah, I do.
You can see there's a bunch that are coming in now. A lot of them are thank yous, and if you notice any that you want to answer, then go ahead.
Okay.
It looks like a lot of them are just thanks.
Yeah, tropical funnel. Tropical funnel, is that new? No. So usually when we get into these environments that are characterized by deep tropical moisture, our atmosphere is moist all the way up. We'll get that, you can walk outside, you can just look up and the clouds are kind of hugging the ground there. Usually we do have a little bit of wind shear with it, but the winds aren't typically that strong. And so what we'll get are these little spin ups, just where we get pockets of instability, particularly if there's any sun that can peek through. And you'll get these brief little spin ups. A lot of them will just be a couple of minutes, very hard to warn for. A lot of times they're tropical funnels and they don't actually touch down. It's really, really common along the coast and a lot of southeastern areas. But we do a couple of times a year get into these deep tropical, moist tropical air masses and can have some of that up here.
Sissy, Raymond, you asked, is there a single person pulling the trigger on warnings, or is there a team input? It's kind of both. So we typically have a primary radar operator who's looking at the radar data, and they're kind of making an ultimate decision of, do we need a warning, do we not need a warning? But at the same time, what we'll do, there's typically somebody else who's watching, a second set of eyes, and they're always keeping an eye on the radar data the same way. And we can seek them for feedback. So if I'm borderline, we're going to issue a warning, we're not going to issue a warning, I can go over to Jason and say, hey, Jason, what do you think about this storm? And then he can either talk me into a warning or talk me out of a warning. And it's a collaborative process. And we have other folks who are there, and their job, it's called mesoanalysis. And they can look at the environment to tell us, well, just like Jason said, this storm is elevated. This storm doesn't really have, it's not in the environment for tornadoes, so it's probably not going to drop a tornado because the environment's not supportive of it. So we can get really caught up in the radar. We have other team members there who are looking at the bigger picture to really keep us focused. So although we have a primary radar operator, it's ultimately a team decision for these kind of things.
I see there was a question on the tornado that hit Garland and Rowlett on December 26th. Was that a product of a supercell split? No, that actually was not a split. The one that, if you remember, those were moving south to north, and the one that moved, I believe, is through Red Oak, and then it went into downtown Dallas. That was actually a new storm that developed to the southeast, and what it essentially did was choked off the one that moved into downtown Dallas. The one that developed to the southeast, which eventually became the Garland-Rowlett tornado, basically destructively interfered with the Dallas storm. So no, that actually was not a split. Those were two individual storms.
I see, Tim, you asked about the wind. How are the maximum winds determined for thunderstorm watches? Well, actually, the watches, they come from the Storm Prediction Center, and they determine what the max hail size and the max winds are. I do know that whenever they're looking at that decision, they're looking across the entire watch box. So if it says hail up to, let's say, baseballs and 80-mile-per-hour winds, that just means that the environment is supportive of that, but not necessarily that that's what every storm is going to have. In fact, most storms are not going to meet that maximum expected or maximum possible limits that are mentioned in the watch. So that's something to keep in mind with these watches when you see those tags.
And I see one that says, can you discuss storm tracks? Are they auto-generated, and how do you determine where the origin is? Storm tracks on any app or GR or anything like that, those are algorithm data, and they are extrapolated from what's called the storm track table. Basically, the radar will identify a storm center based on reflectivity, and it will auto place that, and then it will track that and assign it a storm motion based on its motion. So your storm tracks are usually an extrapolation of that. You got to be really, really careful with storm track. I don't like them. I animate my radar and I can see where it's moving. The problem with storm tracks is if you have a right moving storm or a deviant storm motion, and you just rely on that storm track, the storm may deviate off of it pretty substantially. So yes, that is an algorithm, and if you can just animate your radar, that's the best way to do it.
And be careful with those algorithms, because I know especially on certain apps, they'll throw a little tornado icon if there's any kind of rotation on it. So to give you the false appearance that a storm has a tornado when it doesn't. So for instance, like that Denton storm, where it was not in an environment that could produce tornadoes, the radar, if you look at it, it would say tornado, but the environment is not supportive of tornadoes. So just be careful with those storm tracks. Let's see, Kyle, you asked about, does the primary radar operator decide what mode the radar is going to operate in, and enables the extra scans? And that's okay if you don't remember the acronyms. But yeah, that's typically the primary radar's decision. That one's typically done by the radar operator because they're the one who's intently focused on the radar data itself. So we're looking to see if, Jason talked about the range folded areas. We're looking to see if that range folding is in a storm that we're actually trying to interrogate to see if it's severe or not. Then we can push the PRF back or up so that we would get a better look at the storm. If the environment's supportive of tornadoes, then we decide if we want to do a sales cut or that extra low level scan, and how many do we want. So yeah, that's typically at the discretion of the radar operator.
There is well, it's not really a question, it's a statement. I still want to know why the NWS doesn't let we, the people, see tilts. We do let people see the tilts. Unfortunately, most like your radar apps, like Radar Scope or anything like that, they work off of what's called level 3 data. And the reason why is bandwidth. It's much easier to push out level 3 data to users. Most people will use level 3 data, which is generally the four lowest or 6 lowest tilts. And it's primarily bandwidth. So when you go look online somewhere, they're usually going to have level 3 data. Level 2 data is actually where you will get all tilts, and the Weather Service does make that available. It is out there. If you have GR Analyst or something like that, there's a free data feed to it. Usually you need a viewer like the GR software, but they are not holding it back. It is available.
Let's see, somebody said when measuring winds on radar, how far up from the ground are they measured? That's going to depend entirely on how close you are to the actual radar site. So the TDWR radars, they're typically a couple hundred feet above the ground, right near the ground, but as the further out you go, they can be a couple thousand feet in the air. Typically, if you're looking at radar, you're talking in the neighborhood of a couple thousand feet above the ground. So that typically doesn't always reach down to the surface. So just because you see 70-mile-per-hour winds on radar, it's not necessarily what you're going to get to the ground, but just kind of to drive it home, it all depends on the environment. Some environments are supportive of getting that wind mixing all the way down to the surface, and some block almost all of it from reaching the surface.
I don't know if I see anything else here.
Jennifer, we did have one question that asked about a certificate. So I don't know if people, I don't know if somebody, if they could use CE for some kind of fire safety or emergency safety operator. I saw we had like a 911 operator. I don't know if y'all need to take continuing education courses. Are we offering some kind of certificate or something for this course? Is that in the works? Or could they email us, or how could we do that?
Yeah, we do not have a certificate planned at this time, but if there are some people that are needing it for training credit along the lines that you had just mentioned, I'm sure we can generate something up fairly easily. So sending an email to us or to myself, if you want to drop my email address in there or the webmaster one, then we can handle it through that. That would probably be preferred. So. I did see one question too that I thought was really good, talking about the collaboration between SPC and the NWS chat. Somebody wanted to know if SPC was a secret organization or if they fall within the National Weather Service.
I think I saw that. Oh, I saw.
They're not
a
secret.
What kind of collaboration is there between SPC and local? That's what I saw. I'll briefly chime in on this. So on the day of the Dallas tornado, like I said, their watch probability was only 40%. We can chat with them at any time. The day of the Canton tornadoes, the Van Zandt County tornadoes, several years ago, we were chatting, back and forth, and we're saying, hey, it looks like this environment's becoming a little more favorable for tornadoes. So we can collaborate with them at any time of the day if there's some kind of environmental concern that we think needs to be addressed, or if they think something is changing, they can certainly call us. As far as watch collaboration, that usually takes place pretty quickly. The mesoscale discussion will come out, and then we'll get on a conference call a couple of minutes later if the watch needs to be issued, and we can discuss type of watch and counties and things like that. So it's ongoing process.
Yeah, there's a lot of really good questions. Somebody asked about, are rain-wrapped tornadoes harder to see in radar, harder to determine if it's actually producing a tornado? Not typically. Typically, you can still see it by using the velocity data. I would say it's harder to see in the sense that you're not going to see that classic hook echo that you're normally going to see on supercells and things like that. So that, in a sense, does make it harder to see, but you're still going to be able to see the tornadic circulation on your velocity data. But you're not going to get that hook shape on reflectivity. Let's see, somebody asked about access to the local media radar data. I know Jason's working a lot with the NBC folks to try to let us see the NBC data, but there's just a lot of hurdles that we have to hop through for that.
Yeah, we're a government agency, so nothing is easy. One of the issues with private sector radar data is if somebody owns a radar, or particularly a media company, sometimes that's their radar and that's proprietary to them. If they distribute it to the Weather Service, typically that everything that we do is in the public domain. So there's a lot of legal hurdles there. So no, we don't actually have access to any media radars directly, and certainly not in real time. I wanted to address this one comment real quick. What are the criteria for tornado emergency to be issued? David can comment on this too. His opinion now, a tornado emergency is not really an official warning or anything. It's wording added to a warning. You know, those of you that remember that wording actually came about on the May 3rd, 1999 Moore tornado, where the Norman office put in their warning, this is a tornado emergency. And it was, that occurred back before there was social media and things like this. And it was a pronounced uptick in the wording to get the word out to their media and partners and things like that. And then it kind of took off into this is a really, really bad situation. You need to take shelter. Here's my personal philosophy on it. I did not issue a tornado emergency during the Dallas tornado. I am very unlikely to issue a tornado emergency for a radar confirmed tornado that I am unaware of the actual size and potential for catastrophic damage. I've seen too many cases where signatures look really nasty on radar, but they wind up not doing that much damage. The reason why I did not issue one in the Dallas tornado, even though it was going through a very heavily populated area and it had a pretty nasty signature on radar, was I never got a view of the tornado itself, which is fairly common. Well, I say we get, you'd be surprised how many tornadoes are caught on camera in real time, and particularly in the Metroplex with helicopters and all of this. So it's just a personal philosophy. What I do instead, and what I did on this particular night, was issued the wording, this is a particularly dangerous situation, and then stressed to the media that this signature is really nasty, but we never got real-time confirmation of what was happening. And I think part of the reason for that was because it was Cowboys football night and there just weren't a lot of people out. That's my philosophy. I usually would reserve those for the most, dire of situations. And I don't know, David, maybe you can comment a little bit more on that. But there's no set criteria.
No, Jason, I agree with that line of thinking. And I think a big part of it is that tornado emergency it's the highest level of something that we could do as far as wording and messaging and things like that. So it needs to be reserved for the top 1% of the 1%, so that if you notice or you see us issue it out that tornado emergency, then you know that it's real, that this is the best card. I mean, it's the ace in our pocket, in our card. So that's my thinking with the tornado emergency.
Yeah, there after the Joplin tornado, which was I think it was 10 years ago here, not too long ago. One of the things that came out of the service assessment, and this has come up before, was the overuse of sirens. And there is a real consequence to overwarning. And I threw Scott's tweet out as part of this presentation, not because I was trying to poke fun at Scott and say, ha ha, I'm the expert, but because there is a response to the warning that's issued. And Scott was not personally affected by that warning. So to him, that was a false alarm. And so that's why warning decision is not something that is just done willy-nilly. There's a lot of thought that goes into warning decision making. And if you start throwing out tornado emergencies every time you see a debris signature, things like that, you can really damage your reputation. And I just, I think that's really, really important.
It's important to not, you hit it with the warning fatigue. I mean, a lot of people on this call are more weather savvy, I'd imagine. So how many people, as soon as they get a warning, the first thing they do is they go look outside? That's not what we want. So, I mean, it's overwarning leads to that reaction where, oh, okay, whatever, it's not going to happen. We got 10 warnings and didn't get a tornado. So we're always very cognizant of not overwarning on anything. Severe tornadoes, especially the higher end wording on tornado warnings, especially.
Yeah, there's a question too that says, how is the text of a warning generated? Is it based on a few clicks or keywords and locations, or is it free text for the most part? That's Craig's question. It is all done automatically. So I go click a button that it's called WarnGen or Warning Generator software, and I click on the storm, and I can go back a few frames to get a storm motion, and it puts a polygon, and I can adjust that polygon as necessary, and then I hit create text. There's a template that pops up. And so sometimes you'll notice if you just click it and issue it, some of the wording can be a little funny. I try and clean up the wording as best I can, particularly locations can be funny sometimes in those, but an experienced radar warning forecaster in the heat of battle can get a warning out in about 30 seconds. Sometimes it takes a little longer. Sometimes the wording doesn't come out just right. Sometimes your polygon is not where you need it to be. And it may take a minute or so. But the whole process is very, very quick.
I saw Eric, you've been posting a couple questions. Thank you for joining us this evening. You asked a question, are there more predictable storm systems than others, i.e. QLCS versus supercell? Do they differ? As far as leading up to an event forecasting, I'd say each one is going to be different. So sometimes supercells or supercell events, you got all the ingredients that line up days in advance, and it's just, we nail it. And then there's the other ones where we don't know if it's going to happen until like the October tornadoes a couple years ago. I mean, it's leading up to the event, we think it's possible, but we're still not sure on it. And it really leads up until right before the event before we know if it's going to happen or not. But as far as we typically just forecasting the ingredients, so are the ingredients there? That's okay to forecast. It's not, it's always hard, but it's a matter of, are those ingredients going to line up enough for us to actually get the weather? And I know that's kind of a cop-out answer to the question where it's not really saying for sure yes or no, but it really does depend on the situation.
Ryan says, what factors determine a hail warning for 0.25 inch hail versus 2.5 inch hail? Well, Ryan, I can tell you, I hope I don't issue warnings for 0.25 inch hail. Our warning criteria is 1 inch hail, that's quarter size hail. And we can use different things to determine whether a storm's going to have 1 inch hail or 2.5 inch hail. Sometimes we miss badly, and I've missed many in my career. Dual pole does help for us to be able to kind of see whether or not we've got some large hail in there, whether we've got water-coated smaller hail. Usually if we get really, really high reflectivities, I'm talking 75 dBz or higher, a lot of times that's really smaller water-coated hail that returns a lot of power back to the radar. One of the things that we can use that really does help is called multi-radar, multi-sensor, basically analysis, and that's where we take multiple inputs from multiple radars. It's an algorithm, but it does a fairly decent job in estimating hail size. It can be bad though sometimes. I can tell you, like in an environment like today, what we have, we're not going to get big hail. Summertime environments, we usually don't get big hail because the freezing level is so high and it's so warm that a lot of that melts. There are days where we have tons of instability and very cold air aloft, and we're going to get large hail. But I'm going to tell you honestly, for a radar, for a warning operator, a lot of times you issue a warning based on your best estimate of what may be occurring. And then you've got somebody who says, hey, I got baseballs instead of 2-inch hail. So we can adjust that threshold on the fly and say, okay, I'm going to update my warning here. Or there's cases where you're going, golf balls, and then all of a sudden you get multiple baseball hail reports and say, all right, this thing is producing. Let's up the warning. So.
See, somebody asked about SPC watches and collaborations. David, you hit it pretty much right on. So basically the way it works is the Storm Prediction Center decides that they're going to issue out a watch, and then they'll decide what counties go into the watch, and then they collaborate with us, and then we have the input to say, well, let's remove these counties and add these counties, and then we can come up with the final watch after that. Jason, you see any more questions you want to cover in the last couple minutes?
Have you seen a clockwise tornadic circulation in our CWA? I know they're extremely rare. Clockwise, that would be an anticyclonic tornado. They do occur. I can't recall one. There was a pretty decent one that occurred over in Shreveport's area, but it's been many years ago. I used to have it in this radar interpretation presentation. They are rare. I can't recall of any that I've seen. Now, here's an interesting thing about anticyclonic tornadoes. While they're rare, the velocity signature will just be flipped, but algorithm data will absolutely not pick up on anticyclonic tornadoes. So if you wait for your algorithm to tell you you're going to get mowed over by an anticyclonic tornado, it's not going to happen. So another reason to use your interpretation skills.
Exactly. Let's see. There was one that somebody just asked, and you asked this question, Earl. You asked, any plans afoot for finer resolution for warnings? And that's actually one of the things that I'm involved in, that I love thinking about and trying to think about. What's the future of weather service warnings? There's actually this program called Facets, and what it is, it's kind of creating probabilistic warning. So right now, the way we do warnings, our warning system, we draw a box for either 30 minutes or an hour, and then we wait till the storm gets almost out of the box or towards the middle end of the box, or it's about to expire. Then we issue a new warning for 30 minutes or an hour. We draw these boxes that follow a storm along its life cycle. In the future, there's talk about how feasible would it be for us to issue a warning that updates every 1 minute, every 5 minutes. So instead of, if you're at the end of the box, you get 30 minutes, but if you're right under the storm, you get 1 minute of lead time. So the thinking is, if we're able to do that, then theoretically everybody would be able to get 30 minutes lead time for a tornado warning, or an hour lead time for a tornado warning, or for a severe thunderstorm warning, because we'd be adaptively changing the polygon every 5 minutes. That's part of the future thinking as far as where warnings might be headed. Now, we're nowhere near that happening or being implemented. But that's some of the research that's being done up at the Severe Storms Laboratory to see how can we improve the warning process, and we think that might be a good way that we can do it.
Russell Harper says, how important are amateur radio operators when interpreting radar? Amateur radio operators have always been helpful in the warning decision process. And like I said, it's a process. So there's pieces of information coming in everywhere. Social media has really become a big source of information, but amateur radio operators are always helpful in providing information to us. Now, when we get into the Metroplex, if it hails in the Metroplex, we're going to know about it. That's just the facts. I mean, somebody's going to get on Twitter and tweet, and we're going to see about it. But that doesn't mean that we don't need your reports. Amateur radio has always been a big part of the warning decision, and so those operations. Now with COVID, we haven't had the amateur radio operators in our office, but they have been in our chat, and we've got a direct line to them, so they're still talking on the radios, and we're still getting y'all's information.
Earl, I hear you. It's the size of the warnings. That's something else that we're looking at. So instead of saying everybody in this needs to take shelter, there's talk about making it so you're likely to get hit. You have 50% chance, and you have a low likelihood of getting hit by a storm. So that's all part of the process. But I can assure you that we try to limit the size of our warnings to just those that are likely to be impacted by the storm.
Let's see. Corey says, when I hear tornado emergency, I think of something like Moore, Joplin, or even Dayton. We talked about that, the tornado emergency. And yeah, I mean, that's really what you should think. Those big, massive tornadoes that, you know, you need to do something or your life is, you know, in danger. And that's part of the reason why we don't just throw those out whenever. I'm just kind of going through these, David. I haven't marked any. I don't know how
I haven't either, to be honest. Let's see. Don, you said you asked about the Nashville tornado. That was toughly determined when to warn due to the radar angle. Yeah, I would agree with that it was a toughie of when to warn. I know that storm had a tornado warning. Tornado warning was let go, replaced with a severe thunderstorm warning, and then tornado was issued again after that. That's one of those instances where looking up is a good way to just make sure that you catch things. So that's just something that we all have to keep in mind.
This is an interesting question. There was 5.9 inches of rain in Weatherford today. Was this known to be likely very much, was this known basically in advance? 5.9 inches of rain, probably not. But there was a flash flood warning that was issued. And so again, this goes back, I kind of touched on this in the presentation just a little bit about the changing forecast. It's very, very hard to message, you know, a single message for everybody across North Texas and Central Texas. And so the forecast today was for high rain chances, and I think I read, you know, somewhere around an inch of rain. But there's obviously going to be places that get considerably more rain than that. So then it goes from a forecast to, okay, now we're starting to see rain, thunderstorms, heavy rain, and then the flash flood warning came out for Parker County. And so that's kind of how things evolve. So you go from a forecast to, okay, it's occurring. Okay, now it's really bad here. I need to do something about it. So no, I don't think we had 6 inches of rain in the forecast, but it happened, and we wound up having to get a warning out for it. All right, I'm trying to see if I see any other questions that I missed.
Yeah, somebody asked about storm anxiety. I think the best thing you can do for storm anxiety is just kind of overcome it with education. So by taking this course, learning how to interpret radar, how to just understand what creates storms and how storms operate, that'll be the best ammunition to combat storm anxiety. And then let's see, yeah, go ahead.
There's one: tropical storms, hurricanes, watches, warnings. We only get the remnants here, but what do you watch for in DFW? Yeah, we usually just get the remnants of tropical systems. We can get some pretty strong winds, particularly in our Central Texas counties. The thing that decaying tropical systems bring is a lot of wind shear. So when we have dying tropical systems, there is a tremendous amount of wind shear associated with those. And sometimes we can get pockets of instability, and everything is rotating. So you get low-topped, fast-moving, rotating storms that can produce tornadoes. That's the main thing that we watch out for. Again, algorithms are pretty terrible on low-top storms too. So if you haven't worked an event like that, those can be kind of challenging.
Yeah, I guess, Jason, if you wanted to say what your most memorable event was.
Oh, my most memorable event. So I've been in the Weather Service almost 20 years. I've worked several memorable events. All right, my most memorable event was not a severe weather event. It was the 13 inches of snow that we got here in the Metroplex back in, I think it was 2010. That was an interesting week. That was probably the only day that, well, I mean, that was a rough day. We had like 1 to 3 inches of snow in the forecast, and we wound up getting 13 inches of snow, and all of my conceptual models broke down. By the end of the day, I just threw my hands up and I said, it's just going to stop when it stops. I don't. That was probably the one that beat me up the most. I had no clue what happened. So I worked that one. I did actually deploy and work Hurricane Isaac over in New Orleans. That was a fun event to work. I worked radar on that event, and that was 2 straight 12-hour shifts of tropical tornadoes, and so that was a good one. And I worked the Van Zandt County tornadoes, the Dallas tornadoes. So those are some of my biggest ones, and probably most memorable. I don't know. What about you, David?
Interestingly enough, Hurricane Isaac is one for me too, but I was actually in the Air Force. I was doing weather warnings for a lot of the bases around the Southeast United States. So we were probably working the same storms without even knowing about it. What was that? Almost 10 years ago now. So
Yeah.
that's kind of interesting, but I was working it from a different side of the house. As far as the Weather Service goes, my most memorable thing is also a bad forecast. It has to do with, well, there's two. One, you and I were working, and we had some hail that came through the office. We ended up getting golf ball size hail at the office. And earlier that night, I took thunderstorms out of the forecast. And then about an hour after I took thunderstorms out, storms started popping up and developing. The misses are the most memorable because we analyzed them like crazy to figure out what went wrong so we don't make that mistake again. And then the other one was a lake effect snow event up in Salt Lake City. So I was in Salt Lake before I came to Fort Worth, and that's another one of my memorable events.
Yeah, the misses are always fun. I've had several of those where you pull storms out of the forecast just to have them develop an hour later. It's one of the things I think everybody who's on this presentation is interested in weather, or you wouldn't sit here and listen to us ramble for 3 hours. The public as a whole, though, has varying degrees of understanding of what it is that we do. I know, some people think that we're a government office that has 50 or 60 people and we can do everything, and we shouldn't miss anything. And then it's just not like that. It's like David was saying. I mean, usually when it comes to the forecast part of it, it can be 2 people, 3 people, and then you work several shifts in a row, and you kind of massage your forecast, and it's your baby, and then here comes the day, and this is your forecast, and it just goes it just completely goes awry. And I mean, that's just how it goes sometimes. I think that things like this, having an understanding of how things work, working with good people. We have a great office staff, and being able to adjust when you need to adjust makes things makes things easier, makes things better. And so I'm really proud of the staff that I work with. I mentioned Maddie, she came in and helped me put those CASA images together. We've got a lot of young people that are talented, and it's a really good office. So all of you, who are out there, part of the public and emergency managers, you can you know, rest easy at night that you know, the Weather Watch is in good hands here. You know, we got a really good staff.